falling. Hello, Gustavo, are you going to present remotely?
Yes, and Mark Brown should be somewhere nearby you. He's my
Oh,
co-presenter,
Mark
but I
should be
can't see
here.
him.
Okay,
Yeah,
so
yeah.
and
It's both of us. Yeah, I couldn't make to Japan, but
so
Mark could.
do you want Mark to control the slides or
That's
for
the
the whole
plan.
session?
Yeah, that's the plan. He's
Okay,
gonna be
so
the one
that's easier. We
controlling
don't
the
have to
slides.
switch back and forth, but
Yes.
even switch is not hard. Okay, that we need to make for Mark.
Mm-hmm.
Shall we start first?
Wait, yeah, I can start. I guess someone would have to move the slides for me because it's your stage, and Mark was supposed to be there to move the slides. Oh, there he is. I can see him in the back of the room.
Good morning, everyone. Welcome to the second day of the Linux Plumbers, and especially welcome to the reference track. Our first presentation today is by Gustava and Mark about 1 year experience with kernel CI. Please.
All right. Thank you, folks. It's great to be here. I couldn't make to be at this other side of the planet. It's nice that we have the remote conference, and there is also a bit of time travel to it. For you, it's Friday morning. For me, it's still Thursday somehow. But here I am. Mark and I will be talking about what we've been through in the past year into the new kernel CI. If you've been following what we've been doing in the project lately, you've seen that we've been putting together like a new architecture, that we've been trying to do a bunch of interesting things, and today we'll be covering some of that. Is there something going on in the room? Can you hear me? My mic is super low. Someone is telling me that right now. Let me. Okay. It's not my mic. I think at the maximum volume here.
Extremely quiet though.
Is this better? Well, someone is saying that they can hear me just fine. Maybe it's just the.
Raise your voice a little bit.
I can speak louder. That works as well. That's the maximum I think my system can provide right now. Is this okay? Can you folks hear me? There seems to be some issue with BBB. That Benjamin Copeland cannot hear the room. Or Mark, I think. The remote people can seem to hear me.
Gustavo, oh, that's definitely. Gustavo, could you talk a bit so we can get some levels?
Okay. Can you hear me this way?
That's better.
Okay, sounds good.
All
right, and we can also hear you because your mic was off. All right, I'll restart the presentation and we'll speed up a bit, and I think we can make for those 3 minutes we just lost. All right, thank you folks to be here. We'll be talking about what we've been doing in the last year in the kernel CI project. It's been a interesting ride. If you've been following, you've seen that we put together last kind of a year and a half ago our new architecture, and we've been working on refining it, on making shinier and so on, and bringing more use cases and so on. So that's what we're going to be talking about today. Next slide.
So people are still having trouble. You really need to project, Gustavo.
Okay. Let me bring my mic closer to me. Is this better?
Yeah, that's better right now.
Okay. So I'll talk closer to my mic. That's good. So yeah, let's go to the next slide, and then I'll speak a little bit about the agenda, and then we can move on. So there a little bit about the project. We'll cover user perspective, how you folks can use kernel CI or will use kernel CI in the future. There is also a little bit of a discussion on the technical architecture of the project and some insights on what we're thinking, roadmaps moving forward, and so on. So next. So quickly, I think we can look into the project mission, which is to ensure that quality, stability, and long-term maintenance of the Linux kernel. We've been, since we created the kernel CI project, we are looking at that by the way of building an ecosystem, an open ecosystem, around the test automation, around like the open source project that we have for that. So kernel CI has been like on that mission for I think 11 years now, and we are here to talk a little bit more. I guess we can move into the next slide. Okay, so I guess most of you know we are a Linux distribution project, and we work in the same ways that our other Linux distribution projects in there. We have members. I want to announce ARM as our new premier member. I think that's pretty great that we have big players every year now coming to kernel CI. ARM is one of them, and the next one is next slide. Qualcomm. We're also very happy to have Qualcomm. We want to thank you then for trusting the kernel CI mission and joining us. Yeah, thanks a lot for both members. Next slide, please. And this is our current composition in our Linux distribution project. You can see we've been growing. We got like 4 new members in the past 2 years. Also, Elisa joined us as associate member. So we expect more companies to be joining us. We're not here to sell kernel CI to you, but it would be great if we can convince a little more managers and more companies to join us. So that's next. All right, so what is kernel CI? It is many things, and I think that's one of the confusing parts about it when we start like talking about kernel CI to people. So we've been building a set of services and tools that enable the community to execute tests and to follow results and to understand like the quality of the kernel. So kernel CI would have like pieces that you can use standalone. Like that's the vision we've been building. We have like some of those services, we have some of that tooling, but as we stay together for the coming years, we'll be developing more and more of that. Kernel CI is also a CI system. It's not only a CI system. It's a core thing to us that we're running a CI system, but as I just said, we're also building services and tooling that the community can use on their own for executing kernel tests and validation. As part of that effort to have a CI system and then the tooling, it leads us to the fact that we have a common results aggregator and a common dashboard. You can go to dashboard.kernelci.org, and then you can see what we've been building there in the past like 2 years with the new dashboard. That dashboard has an API which people can query. It's open right now. At some point, I guess we'll have like some user accounts. Otherwise, AI will eat our APIs. And then command line tooling and so on, which Mark will talk more about it later. At the same time, kernel CI is looking, as we do a lot of efforts around testing, we are looking at build certain specs and standards for the community to look into kernel testing. One such effort, for example, was the .kernel CI YAML file that we've been circulating around as an idea and trying to do some proof of concepts is to look into that. And the other interesting thing for kernel CI as an umbrella org, as part of our Linux Foundation participation, we've been looking into hosting other projects that are interested in kernel test and validation process of the Linux kernel. And speaking of that, we can go to the next slide. We are very happy to announce that Thorsten and Hexbot will be joining the kernel CI project. We've been discussing with Thorsten for a while on that. And we know how much the community wants to see the regression tracking process evolve. And we are definitely happy to have like Thorsten and Hexbot. And kernel CI is definitely like interested in investing to the project and sponsoring more effort. We are not going to be throwing a lot of CI regression to it. We know that the key value of Hexbot is the trust that it is built with the community. So we want to do things in a way that consumable by the community. That's not our goal. I think we'll talk more about it. I don't think let's talk about this. Next slide. we're also very happy to bring 3 new projects that are going to be transferred by Linaro to kernel CI. Those are toolings for building kernels, for running tests in virtual environments, and for also interacting and building Lava job definitions for those who are doing like embedded testing. That's great. And some of that tooling we are integrating to our core architecture. And I think it's gonna empower kernel CI to do more into the future. All right, next slide. And well, who do you work for? Who is our audience? Like, it's all the people that wants to do testing, that want to add or improve testing to kernel, the ones evaluating tests. I think that's like the group of maintainers, the upstream developers, hardware vendors, product makers, and I think a few others like lab operators and so on. That's like our core audience. And I believe that core audience is sitting right there in front of Mark. So I'll be handing over now to him to talk to you about the things we've been doing.
Thanks, Gustavo. So as Gustavo said, part of the reason I'm taking this bit of the talk is that we're anticipating this might be where many of the questions come in. So if you have any questions, feel free to raise your hand or whatever and jump in as we go. No need to wait for the end. So the core thing with kernel CI, as when you're looking at using it, is that it's not intended to be just a fully packaged solution that you have to take and use exactly as we've prescribed. The goal is to provide a toolbox that you can draw from to either build CI that you want, share your results with the rest of the community, or maybe just it will do everything you need. But the goal is that it's not saying, here's what you must use. It's saying, here are some things you can pick up if you want to use them to help build your CI or to help your CI work better with the rest of the community, then here they are. This has all been growing out of requests from interested users, from other people working on CI. It's not really, the focus hasn't really been on trying to design something greenfield and hoping that it delivers for people. The goal's been on to listen to what people have been asking for and to try and meet those needs. One thing I want to be clear with about this, in the spirit of it not just doing things, is that it's not some automated bot that's going to start sending huge amounts of reports to your list. That said, in the spirit of it being a toolbox, if you want a bot that is going to send huge amounts of test results to your list, kernel CI will absolutely provide the tooling that will help you do that. I don't know why you would want that, but you can have it if you would like it. The goal is to help bring together test systems, to pool knowledge, to pool resources, and help people who want to look at testing to see things collectively and avoid having to learn too many individual CI systems. So, as an end user, as an end user of the system, there's 3 main ways that you would come to kernel CI to use it. There's the web dashboard that Gustavo mentioned. That's built on top of a web API, which is also available for people to use. That lets you view the results we've got and analyze them. We also support email notifications on test regressions, and we can summarize the status of trees on a regular basis if you would like. And finally, there's a tool called KCI Dev, which is built on top of both the web API and the internal APIs we use for test generation. That provides all the functionality of the dashboard, plus more. It's got facilities for triggering new test jobs. In particular, it supports bisecting test results or bisecting tests using the kernel CI infrastructure. So the dashboard, as Gustavo mentioned, it's at dashboard.kernelci.org. Because I'm a coward, we are not going to do a live demo. We have some screenshots here. But this is the view you see when you look at an individual tree on the dashboard. Can you see my pointer? Yes, you can. Good. So we have summaries of the build testing we've done, the boot testing we've done, and the runtime testing we've done. These all look very similar. We've got some graphs at the top which show how the status is changing. And then we've got lists of the configurations, the hardware, and further down the tests we've tested, which you can use to filter down, and eventually you will get to an individual test result. And the individual test result has details of the of what was run, both the build and the hardware it was run on, exactly which commit was tested. So is that a question? Oh no, sorry, it's not a question. It's people talking. Links to the logs showing the output of the test, and a quick summary of how the test has been performing recently. That summary is also available in the email reports. The regressions report looks like this. It shows a test that started failing, a very brief summary of it, and a link to the detail page for the test, and a quick at-a-glance view showing when the test has been passing or failing. Just giving you an indication: is this a test that's flapping, or is this a test that's likely to have actually regressed? And we also summarize if things start working in the same format. And finally, KCI Dev. Again, not going to do a live demo, sorry, just a quick screenshot. You can find all the details of KCI Dev on the kci.dev website. This was written by Arisu Takibana, who I don't see here, but she will be talking about this later on in the testing track. So if you want a deep dive into KCI Dev, go there. Like I said earlier, it provides all the facilities you get in the dashboard, plus the ability to trigger new tests and automation for tasks like bisection. So how does this all fit together? Everything we're doing at the minute revolves around the database. The database stores all our test results, the details of what we've built, what we've run, what other people have built, what other people have run. So that's then used by the web dashboard and API to provide a read interface that people can use to see what's happened, look at the status of the various projects. There's an ancillary storage server, which means we don't store things like full test logs or test artifacts in the actual database. The thing that that schedules all the testing, monitors the trees, works out what to build, what to test, is called Maestro. That's another service. It looks at Git trees, or it takes in builds that are requested through an API. It stores the details of what's being tested in the database, and then it runs test jobs on hardware labs which are contributed by a number of third-party providers. Kernel CI itself doesn't actually have any test hardware at all. It's reliant on donations from the community for coverage. If you're interested in doing that, speak to us. We always welcome new hardware contributions. We also have other test systems that monitor the builds that Kernel CI does and schedule their own tests independently. These push data back into Kernel CI using our APIs, so their results are visible in the dashboard. Some of these systems also push in results that they've generated completely independently of Kernel CI without any involvement from us, just to use the result aggregation support that we've got, so they don't have to write their own user interfaces, for example. And yes, KCI Dev uses those APIs to generate its own build tests for for things like bisection. So this slide is basically just a summary of what I just said, pointing at the diagram in words. Give you a moment to look at it if you want to read it, and move on. So this hopefully all sounds great. You're hopefully all really excited. I can sense the enthusiasm in the room. But I don't want to oversell what we've got here. Is kernel CI ready for your needs? Maybe it isn't. It's a concrete system. It has finite resources. It has a fixed set of features. Maybe those deliver everything you need, but maybe they don't. But we're actively working on developing it. So maybe it doesn't deliver what you need now, but maybe it will. Talk to us. Testing is, as I assume everybody in the room is fully far too aware, a very hard problem. We're constantly working on trying to build out what we've got, on trying to understand what people need from a testing system, and trying to do things that ensure we can meet those needs as well as we can. One of our big goals is to get everybody working together, sharing effort, sharing resources, and propagating best practices out through the community so that it's easier for people to start doing testing. It's easier for people to start relying on testing. It's easier for people to start building new testing that they want. You know, we're doing that with the default tooling we're providing. We're doing that with the storage system we're providing for propagating data. And we're trying to define standards and best practices for people to use. Gustavo just showed you a bunch of the projects that are coming together to work with us. Things like RegSpot are particularly exciting. We're working with them. We're looking to build out the features they need and improve kernel CI so that it's better for everybody. So if you take a look at kernel CI, which please do, and you see that it doesn't meet your needs, first, please talk to us. We can't promise that we're going to solve all your problems instantly, but we will make an effort to do so. And also, of course, this is a Linux Foundation project. There's centrally funded development and so on. If you're working in a company and you think kernel CI is useful for you, speak to your manager and your team. See if you can encourage your company to work with us as well. So as I've been saying, please come and talk to us. I'll hand back to Gustavo to talk about the various ways in which you can do that.
All right, thank you, Mark. That was a very good show of what kernel CI is doing now. So yeah, we have a few ways you can talk to us. We have our GSC members. I think unfortunately only Mark Brown is there in person at Plumbers right now, but we have all other folks that you can reach out and talk to them anytime. We are happy to hear from you. There is, as usual, our main list. For the new kids, there is Discord, something that we've been using, and we've been very happy about how it's enabled the community to interact far more on a day-to-day and discuss like a bunch of the issues that we are facing when we're developing infrastructure, when we are solving certain issues for maintainers. But we always will have a RC channel for you. You can join kernel CI on the beta. And we'll be there to answer questions and to work with you on solving doubts on the kernel CI, on taking ideas, feedback, and so on. So yeah, please talk to us. We want to hear from people. Next slide. So I think that's kind of trying to summarize what we've been discussing here. Like as I said in the beginning, kernel CI, I think we started as a CI system back then, but we've been looking to really consolidating as much as possible of the Linux kernel testing and integration stories that we see. We have, for example, Greg asking us to develop a process where people can report their stable C test results through kernel CI, because right now he's getting like a different email reports on that like 2-day window for the stable C process, and we want to see like one at some point, that's his dream, at some point like have one report or one system that can give him like the insights about the stable C, so that like is saving him time, and it's also consolidating a process for the community to report results to the stable team. So I think that's like that's how we want to be enabling an ecosystem of test systems to contribute to common goals. Like we all want to see like a better pull requests with better testing. We want to be identifying like the regressions as early as possible, because that will be saving a lot of time from the maintainers, from the developers, from the people building products, from everyone really. So kernel CI wants to help that data flow. That's like our main one of our main goals. And as we discussed it, acting as umbrella for projects. If you are interested and want to discuss with us, if you have ideas and you want to understand how interaction and participation in kernel CI could become like a win-win situation for both projects, I think we are definitely open to it. Kernel CI, as we have like member companies who are paying their yearly fee, we have budgets where we can sponsor certain activities that are aligned with kernel CI goal. Like for example, dashboard is something that we've been sponsoring the development for almost 2 years now, from the API, and then from doing the database, KCIDB under 8, and we are looking to sponsoring other activities the next year. And the more companies who join us, the more we can sponsor. It's really like trying to consolidate a place where we can manage that kind of infrastructure for the community. We can manage the resources, and it's also like liability, because if you're running a lot of like cloud servers out there, or you are dealing with like a kernel testing and doing that in the open, there might be risks, and the Linux Foundation is there to provide us the liability in that as well. So that's kind of where we are targeting, like in the long run. It's really long-term project. Like look at the Linux kernel. We've been here for 34 years now. Kernel CI is trying to navigate to build this infrastructure in the short term, in the medium term, in the long run as well. Next slide. So what's next for us? I'll just give a quick overview of what we've been doing, and then we can go into questions. I think we wanted to make this shorter so people could come up with their comments and questions to us. We just elected a new TSC with names that we just showed in two slides ago. And that's like a quite active group that has been meeting every 2 weeks to discuss new initiatives, to discuss which working groups we should be kicking in. One such working group, for example, is the labs working group that's helping the community with a new API and implementation into our core orchestrator Maestro to facilitate different organizations and people to connect themselves as a lab. Maybe you have like a few boards there that you want to connect with kernel CI, or companies want to do that for their products. They have a better way to do that in kernel CI moving forward. We are also looking to bring in bisexual functionality. It's unfortunately a quite complex problem when you look at the scale of like CI testing, but we are looking to that. The dashboard and the backend API powering the dashboard is something that we are actively developing. There is a web dashboard working group that's every 2 weeks is defining the goals and priorities for the dashboard team to work on. On the dashboard, we also have email notifications. We've been having contributions from some of our members like Qualcomm on improving the notification system, and I think that's a key part, and I think it speaks to what Mark was telling you a few minutes ago, that we don't want to be the next bot that's going to be throwing a lot of emails into the main list and flooding everyone. So we've been growing these like really in a very careful way, I would say, like to not like get into the position where at some point you're just like throwing thousands of emails every day. Right now it's a subscription first. You have to go into the repository, add a file, a YAML file with your email, what you're interested in. We are growing the options to which you can subscribe to. Eventually, that might be happen through the API or through KCI Dev that you can subscribe to your notifications. And I think a key element there that we want to look into that more in 2026 is the quality of the data. It doesn't help if we have like thousands of tests every day or every week, but we don't know how to separate like which one are the good tests, which one are flaky, which one might be coming from, you know, some hardware issue or some infrastructure issue in the lab from the real regressions. So I think that's kind of like where we are looking for making significant progress into next year, so we can start reporting more regressions. Because right now we don't report that many, because if we do, it might be that we want to be reporting to you things that are not a regression, and that's a way to very quickly lose the credibility and the trust that the community is putting on kernel CI and projects under the kernel CI umbrella. So we definitely want to be focusing on what the community wants to see, how they want to track regressions, and then fit ourselves into that process. So there is like a lot of background work that we've been doing to get there, and we will continue doing that in 2026. Next slide. That's it. Thank you. Questions?
So hi, Mark. This is Trilok Soni from Qualcomm. And so one of the questions I keep getting actually from various other teams when I report the results back to the web dashboard, we have a fantastic set of proprietary test cases which we run on Android, Yocto, and for various reasons, right? So multimedia blocks and connectivity blocks. And they do find really nice kernel bugs over time. And the question was that, okay, we may not be able to open source it right now. Can we still test them with this, our Qualcomm lab connected to this kernel? And can we report the results back with enough information, which enough is again debatable, but can this be also be kind of allowed? I think I asked this question on Discord. The answer was a little mixed, but someone said, yeah, it's okay with enough information, but I still want to kind of throw it out here because I didn't get a conclusion on it, saying that what should we, right now it's all open source test cases we run and we report it back. But I keep getting this question.
Gustavo, do you have...
Yeah, I can take that. I believe, and maybe that's like some. If you want a decision on that, I think we have to take that to the TSC and look at that. My opinion on it, I would be happy to see your results in our database. However, I don't believe a maintainer would be happy if we report to them a bug that you found, but you don't show the code on how you found that bug. So there's a limitation. I'm not saying that your code shouldn't be there. It might be interesting to see your internal data to validate that the kernel is going in the right direction. But we have to understand, and maybe that will mean that we have to implement some certain tagging mechanism. I mean, something simple, but something that will flag those tests as something that can't really be just sent out to maintainers to fix, because they won't fix your proprietary use case, right? But I think that's doable. And then it might also allow you, if you want to add into that process, you could come up with maybe a reproducer, or maybe when you see a regression, you can open source exactly that bit and then work with the community. Like that might be a path for you to do more open source of your testing, for example.
Thank you.
Yeah. Just like speaking personally and adding to what Gustavo says, I think from my point of view, a non-public test isn't hugely different to a piece of hardware that's made of unobtainium, and we're clearly we do as a community accept that people will have hardware that they can't give us or that we frankly don't want to have. So I think it's something that should fit in the umbrella. Like Gustavo says, maybe we need some filtering on for people who don't want to look at it or for where it causes difficulties. But it's not for me. It's not a fundamental problem at all.
And that's like a inside the whole idea of the CI ecosystem, like in that architecture box, because you can have your test system and then you report some part of it as open public results. Some part you won't report because it's your next shine hardware, so you don't want to tell us that. And then some parts is proprietary tests, and we flag that as something that we are not going to be sending to reports. But if people go through the dashboard, there might be ways for them to see them that.
Okay, thanks for the talk. So for the sanitizers, we have a bunch of KUnit tests. I checked the dashboard. Apparently, they're not at kernel CI yet. So how do we onboard them?
We need more effort for people to enable the tester. We have some KUnit, but I don't think they were enabled in the best way possible when the new architecture was being created.
Thanks.
But we are happy to chat about it for sure.
I just wanted to respond as an upstream maintainer to the question about proprietary tests. I think from the perspective of someone who might be asked to work such an issue, there are two parts to the problem. One is understanding what's going on that actually caused the failure. And it might be that even if the source code to the test was proprietary, if, for example, you could give us the strace output so we could see what system calls were being issued, that might be one of the things that the upstream maintainers might want. The other really key bit is if we don't have the test binary, we need a way of validating whether a potential patch actually fixes the problem. And that's where it kind of impinges on the CI piece. If you take a look at Syspot, one of the things that Syspot does, which is very handy, is even though they give us the source code to the reproducer, sometimes it doesn't reproduce on our hardware. And so there is a way in which we can ask Syspot, here's a patch. You were able to reproduce the problem, even though I'm not able to reproduce it using my hardware. Please try this patch and let us know what you see. And so it may be that there are some discussions that we can have about if there are companies with proprietary tests and you're hoping to get engagement with the the upstream community, there are ways that we can make that work in the CI context. Now, how much of that is kernel CI versus some other system? I think we'll need to figure that part out.
And I think that's one of the things that the ability to trigger tests in KCI dev could help with. You can ask us to run a test for you, which will hopefully get into the results.
Can you share some success stories of kernel CI? In particular, I'm interested in kernel CI as tool provider, what tools are used by other CIs and how, and second part is kernel CI is an actual CI in the same number of regressions prevented.
Yeah, so the database has been fairly successful in terms of getting people to push data in, and people do use the web dashboard for these for the other CI things. Like for example, I have my personal stuff that I run completely independently, and I use the kernel CI web dashboard to look at that sometimes because I'm not going to write a web interface Somebody else has done that. That's fantastic. I can do that. I don't need to use any other bit of this system for it. And we've also got Gustavo mentioned that ARM recently joined. I work for ARM. We actually have a deployment of kernel CI internally. So we've just taken the entire software stack, dropped it onto our network. And it's the basis of our functional CI for for the upstream kernel development.
Yeah, and when it comes to regressions, we have like a bunch of successful cases of reporting good regressions, build regressions, and people fixing it or diving into to understand what's happening to their kernels in kernel CI. Or Greg dropping a bunch of patches from stable C when we report those issues to them.
So just to answer that question, we just recently discussed in a TSC about encouraging more uses of kernel CI reported flag, kind of a line in a commit text when you're submitting, so that we can easily track that, okay, this was reported by kernel CI, we found it from there, and so that we can account that all these issues and maybe improve more test cases around that as well. So yeah, I think that's an active discussion in TSC as well recently. So yeah.
One last question.
Okay, thank you for the talks. And then, if I'm wrong, please correct. So one feature I think missing when I look at the kernel CI in the past is the feature to trigger the tests for each patch post. So my understanding is that Maestro has a role to trigger the test runs, and then I hope that it can connect it to the patchwork, which manages the patch post status. And then if kernel CI supported, Maestro supported, that's great. So what's the current status?
I don't. That's definitely something you can do. Like that's the whole KCI dev trigger blah 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 thing that I've been mentioning. I don't think we've currently got any patchworks that have been interested in working with us. But is anybody? We were talking to anybody about that, Gustavo?
We don't have any patchwork. We've been discussing patchwork integrations for with a few folks. We don't have any right now. What we have is a NetDev CI integration where there is hardware in the kernel CI labs that is being used to validate certain use cases for the NetDev CI side of things. But for patchwork, we're still missing that. We don't have it. I think one challenge there, if you want to like build every patch, I don't think we have the build resources for that.
Yeah, and I think I think we also need some patchwork using project to step up and work with us on that. We'll need something on the patchwork side to do with the triggering or to help with the triggering probably, or at least somebody who's happy for us to sit there and hammer the patchwork API and not cause them load. So it's doable. It's if you've got a patchwork that you want to test in this way, come talk to us. We'll see what we can do.
Okay, time is up. Please join me to give another round of applause for our speaker and our great work with kernel CI.
Thanks. Thank you.
Just in case. I need to power that on. Oh, you can power it off now, maybe. Okay. 5 minutes. If you go at the end of the time, you want it at 40 minutes or 35 minutes? Because you want like 5 minutes for questions. If you want 5 minutes plus another 5 minutes to finish up, or I can give you the 5 minutes at the 35 minutes. So which one? Which would you like? So I'll give you 5 minutes, meaning that's 35 minutes. So you have 5 minutes to finish and 5 minutes to focus questions. Yeah, 45 minutes. So I'll give 40 minutes presentation, 5 minutes question. That's ideal. So I can give you a heads up of 35 minutes. So you have 5 minutes to finish up. Then we have 5 minutes for questions. This was 35 minutes. And then okay. Hello, everyone. It's time to start. My name is Byung-Chul Park, and I'm here to introduce TAPT tool for deadlock detection. I will start with introducing what deadlock is, how deadlock occurs, and go through what LockTap is and how LockTap works, and what TAPT is, how TAPT works, and I'm gonna finalize with introducing the benefits of using TAPT. Introduction. Imagine code like this. Can you see the deadlock condition in this code? These two contexts required to acquire two spin lock A and B, but in opposite order. It's a typical ABBA deadlock condition. With a simple code like this, it's not that hard to track deadlock condition, but with the code using complex synchronization mechanism, it's nearly impossible to track deadlock conditions by hand. So we need a checker tool to check lock acquisition order. Of course, it'll be much better if the check can be done before the lock happens. In this presentation, I'm going to talk about runtime checker tool that hooks into synchronization mechanism to check and report. Like that. The first tool I'd like to introduce is LockTap, developed by Ingo. LockTap defines dependencies this way. So when acquiring lock A and lock B while still holding A, it indicates that A depends on B. So in this code that I showed you earlier, by the definition, context X has A to B dependency that can be added to the graph data structure in global space like this.
And similarly, context Y also has E to A dependency that can be added to the graph. Using graph algorithm, a cycle can be detected. Circular dependency means deadlock conditions. So like the tool can report it as a problem, like potential deadlock condition. Okay. System might have dependency graph like this. Once Y to Q dependency is added to the graph, then I can detect the cycle and can report it as a problem. All right. Let's look at more complex code. Before going ahead, I'd like to remind you of the definition by LockDep. To create the dependency, 2 consecutive lock acquisitions are required. So in this example, only context Y has 2 consecutive lock acquisition. Right. So in this example, only C2A dependency exists by the definition of LockDep. So LockDep only can see the C2A dependency, and that can be added to the graph. But since there's no cycle, LockDep doesn't report anything. But these 3 contexts are stuck at the highlighted points. For a wafer event B to be awakened, event B must be triggered, but that can only happen if mutex lock C is successfully acquired. For mutex C to be acquired, mutex unlock C must be released by the owner, but that can only happen if mutex lock A can be successfully acquired. For mutex lock A to be awakened, then mutex unlock A must be released by the owner. But that can only happen if wait for event B is awakened. Again, so these 3 contexts are waiting for the events that will never happen. So not only typical locks, but also wait chain event can lead to deadlock. So it's very important to consider general weight, not only typical locks. That. The second tool I'd like to introduce is that I've been developing to expand the coverage. Let's look at the context part. To trigger event A, wait B must be awakened. For wait B to be awakened, event B, that event B is waiting for, must be triggered. By deductive reasoning, we can conclude to trigger event A, event B must be triggered. So I can say event A occurrence depends on event B occurrence. So instead of the previous definition that is used by LockDep, I'm going to use the new definition. So when event A occurrence depends on event B occurrence, I would say A depends on B. Okay, this is the simple example that I already showed you at the beginning. I will change the comments to reflect the perspective of depth, but leave the original code unchanged this way. Spin lock is a kind of a wait that is waiting for the target lock to be released by the owner, right? And spin unlock is a kind of a event for its wait. So I want to tell you, remind this diagram in mind to analyze the dependency. So here, I can say A to B dependency exists because spin unlock cannot be called unless the event the spin lock B is waiting for is triggered. So that can be added to the graph in the global space. Similarly, context Y also has B to A dependency that can be added to the graph. So by using graph algorithm, a cycle can be detected and depth can also reported as a problem like that. Okay, this is the more complex example that I showed you where LockDep couldn't catch the problem. Let's look at if depth catch this problem. I also changed the comments to reflect the perspective of depth, but keep the original code and change it like this. Okay. By the new definition, context X has A to B dependency that can be added to the graph. Similarly, context Y also has, as I told you, mutex unlock is kind of an event. Mutex lock is kind of a wait. So C to A dependency exists that can be added to the graph. And context G also has B to C dependency that can be added to the graph. Using a graph algorithm, a cycle can be detected and that can report it as a problem. Okay. The system, I told you the system might have a graph like this. This dependency graph can be expanded thanks to the additional dependencies that comes from general weights rather than typical locks, allowing depth work better with richer dependencies. So once N2G dependency is added, it can detect the cycle and it can report it as a problem. Okay, I'm gonna talk about how depth works in more detail. When it comes to weight, it's not sufficient to merely put weight A into weight state. To ensure the weight to be awakened, before putting the context X to the weight state, the context X must require context Y to start progressing toward event A so that the event eventually can be awakened. Okay, between a starting point and event A in context Y, there might be some weights that prevent the target event from being reachable. In this case, it's weight B. So with these relationships, Depth can analyze the dependency between weight and event. And depth label each part S, W, E respectively. By understanding what the label means, we can interpret the output of depth better. In this diagram, S, W, E label can be labeled this way. Okay, now that you have a brief understanding of what depth is, how depth works, let's look at what depth can do in practice. Okay. This is an email from LKML mailing list. A Japanese developer reported a deadlock condition between PG locked and NI lock in NTFS 3. Unfortunately, LockDep couldn't catch the problem because PG locked behaves more like general weights rather than typical locks. So Linus Torvalds asked me if that can detect this problem. So I checked and replied to him with captured report. The highlighted core paths are the ones that we are interested in for this issue. This is the reply. Depth successfully captured problematic core stacks as I expected. I think it was cool. This is another example. An Igalia developer, maybe, yeah, he reported the deadlock issues involving folio locks and a mutex. Unfortunately, this also cannot be detected by LockDep because folio lock use PG locked internally. As I told you, it's behave more like general weights, so it cannot be detected by LockDep. A memory management subsystem maintainer, Andrew Merton, asked me if depth can catch it. I asked him to catch the problematic curse text if possible. Thankfully, he replied with captured report. Yeah, the highlighted the course text core paths are the one we are interested in for this issue. This is his reply. Depth successfully captured the problematic course text. Yeah, I was happy to see this one. Okay, let me introduce benefits of using depth one by one. Depth focus on weight and event, which also cover typical locks. As I told you, typical locks also kind of a wait for target lock to be released, right? And unlock as a unlock of owner as an event for its weight. As I mentioned, folio lock behave more like general weight, so it can be covered by depth that track weight and event themselves. And depth also support wafer completion complete and any types of general weights and event. For example, TMA fence or something like that. Okay, the second, depth provides APIs to directly annotate weight and event. Honestly, it's more for advanced user because I already added appropriate annotations to all the synchronization, all the existing synchronization mechanisms. So if you are build a new synchronization mechanism, or if you want to add annotations, annotate wait and event at a high layer, then you can find these APIs useful. Okay, and 3, tap the track, read, write, lock simply with no clever tricks. That means LockDApp need clever tricks to track, read, write, lock. LockDApp consider all possible cases of 2 consecutive lock chains to track read, write locks. LockDApp categorize lock chains into 4 types of chain: SR, ER, SN, EN. So shared leader followed by recursive leader, blah, 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 blah. And it enumerates all possible cases of lock chain types. And it consider only valid cases that contribute to deadlock actually. This is how LockDApp works for read-write locks. However, that just the focus on wait and event, even for read-write locks. Okay, let me give you 5 seconds. Which statement is false? 1, 2, 3, 4, 5. Okay, as you know, yeah. Of course, yeah, sure. Really critical sections can be executed simultaneously, as you already know, since read lock doesn't have to wait for other. There is a question.
No, you're wrong. If the lock is fair lock, then a read lock can wait another read line lock because there is a writer waiting on that. That's why LockDApp has a trick that you said that doing this. You just detected if there are 2 fairless read lock, they may block each other because there is a separate write lock waiting in the same time. Because of fairness, you cannot give read lock like infinite priority, right? If one read lock holding lock, and there comes a write lock, and you have to give the write lock the next lock. Is that clear?
Sorry, I'm not. It's my bad, but I'm not used to the accent you have. Can we talk? Fine.
I think his point is that once you acquire the read lock and there's a writer, the second reader cannot acquire the read lock anymore because the writer is on the queue. So once the reader unlocks, the writer is the next one, and the reader has to stay away until the writer goes away. Is it correct? Yes. That's a different one. I think there's an exception for the semaphores to only happen if an interrupt context happens. So it's not in process context, and it's only done in interrupt.
If you don't mind, can we talk after? Okay. Anyway, thanks for the comment. I want to discuss offline. Okay, so read lock doesn't have to wait other read critical sections to end. So the first statement is false. So I want to tell you how that handle read-write locks. For mutex unlock A to be called, read lock B must be awakened if it's in a lock contention. The event that can awaken read lock B is write unlock B. So here, by the new definition, A to B, more precisely, A to write unlock B dependency exists that can be added to the graph. And this is write lock cases, write lock case. Similarly, for mutex unlock A to be called, write lock B must be awakened if it's lock contention. And the events that can awaken write lock B is either read unlock B or write unlock B. So it has two dependencies, A to read unlock B and A to write unlock B. So these two dependencies can be added to the graph. Ultimately, read-write locks also wait an event after all. So by tracking dependence this way, that can cover all the possible dependencies, including typical locks and read-write locks and general wait as well. Depth support multi-report. As you know, lock depth halt after a report. We must resolve each issues sequentially to proceed to the next. But depth doesn't stop and keep generating all possible reports in a single learn unless the memory is exhausted. Yeah, that's, I think, the benefit of using that. Okay, we near the end of the presentation. I imagine some of you might be wondering. The first one is, you might want to ask, do you intend to totally replace LockDep? My answer is no. LockDep doesn't perform only dependency check, but also lock usage correctness check. I think dependency check should be replaced, but the lock usage correctness check should stay. This is what I'm thinking it should be. This is the current state versus the desired future state. Currently, lock depth and depth performs their checks separately, but I believe in the future, depth must take the full responsibility for dependency check with lock depth, utilizing depth engine for dependency check. Okay, second question. Lock depth halt after the first report. So any later valid issues get buried. False positives make this even worse. That was the biggest obstacle to adopting cross-release. So step to handle this better. I think I need to give you a brief introduction of what cross-release is. That was the first attempt to expand the coverage, implemented as a LockDev extension, but failed the region as described in the first sentence. My answer is, as coverage increase, as inevitable that the number of false positives also goes up. Yeah, sure. False positives still need to be fixed, but since they have to support multi-report, they are no longer fatal to adoption like cross-release. Yeah, but yeah, right. False positive still need to be fixed. Okay, you might ask, why don't you resolve all the false positives first? My answer is like lockup, which has relied on annotations to avoid the false positives over the last 2 decades. That tool will require the annotation report. I think the performing the annotation works within mainline will help us to add annotations more appropriately, and will also make that useful tool for wider range of users more quickly. So yeah, that's my answer. Okay, question 4. You might ask, why don't you develop that as LockDev extension? My answer is reusing breadth-first search algorithm and hashing is a advantage, but all other parts need to be rewritten to reflect the perspective of depth, since that was originally designed to track lack of collision order, and it doesn't fit on weight and event model. So it's my answer. Yeah. If you have any question, please ask me. And it would be appreciated to speak slowly because yeah, it's my bad. But
yeah, I wanted to know the can I see the lock dependency in the CCFS or other interface, not from the log or other things? Can I see from some other interface?
Yeah. LockDev also has an interface that we can use to see the dependency that has been detected since the system booted. Same as LockDev, TAPT also has the interface that we can use to see the dependencies that comes from general weights and locks.
So I can some system status for the some lock dependency in runtime. Oh, yeah.
Yes, right. Yeah. I rather say weight event dependency rather than lock dependency, because TAPT focus on weight and event dependency. Yeah.
And in the some slide for the some read and write lock. So I'm curious about some writer starvation and from the status some complex some logic in the RW lock. So I think it is hard to a simple definition, because as you know, Byung-Chul, there is a fairness logic in the RW lock in modern Linux kernel. So can I detect the some starvation or some dependency from the too many read lock and other things?
It doesn't detect starvation. It only detects hang caused by dependency problem. So I think the starvation is not the problem that comes from dependency issue.
Yeah.
So currently it's not the target of that.
I actually wanted to ask something similar, because it's not from dependency a problem, but starvation is generally a problem from performance point of view. So detecting starvation is really good. And it's actually, I was discussing yesterday in the PI. I wanted it in the user space, but like having something in the kernel space, because sometimes you need to do a performance boost to fix the starvation issues, which are critical to performance. So it's not correctness issue, but it's performance problem. That if we can extend it to help detecting starvation, that will help us maybe to fix these problems as well.
Sure, it'll be helpful.
So if there is a path, it will be good to know what's the path
Yeah.
to get the starvation.
Yeah, then I need my think another approach to
Yeah,
that. But for now,
I think there's another way of addressing that, which already exists,
yeah, right.
which is lockstat, right? I think one of the real challenges with performance problems in general, and locking starvation, locks that are being held too long, is it tends to be very dependent on the workload and the hardware configuration, as in the number of CPUs that you have. And maybe if you're under high memory pressure, it might trigger certain types of locking performance issues as well. So these tend to be a little bit trickier to find and diagnose because of all of these workload and hardware configuration specificity issues. But I think lockstat is the solution to address those. When you actually know that you have a problem, you may need to address it replicating the production or customer environment and production and customer workload. But that's that's something that the Linux kernel has had for a very, very long time.
Yeah, but to be honest, my interest is mostly on the weights because that's hard. For locks, we are having proxy execution. So like it will help basically to address some of these issues, although like it's not really starvation if there is no dependency for the waiters for a long time. So like it will give a boost, but I wanted this weight to be in production. So like to do some mitigations. So if like somebody is waiting for an event and this other who's not sending the event taking a long time, and we can detect the starvation, we potentially can automatically like, hey, maybe the host since the event is being stuck because of like it's not being scheduled in time, it's running at a low frequency. So we can do some sort of boost to help these cases. So that's why I was asking, basically.
Yeah, along with the lockstat, I think the problem of lockstat is too heavyweighted, so you cannot enable in a production system. So we have lock contention trace points for its intention is to enable in the production system. So it has a hook in only for the slow path of the locks. So you enable it for tracking the contentions and how many contentions. Maybe it can be used to detect starvation kind of problems. But
I think for locks, starvation would be nice, but with the proxy execution, I hope this will disappear because the lock waiters now will steal slice from the holder and basically help them progress and release the locks sooner. But the wait, which is really what's the nice thing about the DEPT, it's like as the wait, which is really something really hard to detect. So if we can have something that can be production ready to allow us to detect this, then this will allow us to basically do some mitigation similar to the proxy execution, although like simpler mechanism, like just boost the event sender just to basically unblock the waiter. So that will be great, like because that's a harder problem to fix. With lock, you can get the dependency chain very easily, but like so proxy execution can fix it. But with wait event, it's hard to get the dependency chain. But if we can get it and then add starvation detection, then maybe we can ask for an action to help fix the starvation issues.
Thanks for the great comment. Excuse me, my laptop is locked.
Oh.
Can you?
Oh, I can. Yeah, kind of just like wondering, do we really need to put this into the kernel? I did a similar thing, but for the user space, and the only thing that we did, we enable uprops and then BPF. I couldn't do the same for the kernel space because most of those completion APIs, spin locks, and so on get inlined. So, and that's the problem. But if we stop inlining them, then we can attach kprop, and we can attach a very simple BPF program that will simply emit a very short fixed-sized event every time this happens. But then you can run all sorts of analysis, whatever complexity in the user space, or even post-analysis, and so on and so forth. So I've been wondering if if that could be actually one of the possibilities, one of the directions, because having this in the kernel puts a lot of complexity constraints. It puts constraints on memory and so on and so forth. But if you do this in user space, and emitting BPF event is a very lightweight thing to do compared to logdep or logstat and as such.
Yeah.
So I may have some comments on that. So I think like with like spin lock, a lot of them, they are just inlined into the caller. So it's not easy to trace that afterwards without changing the kernel.
As much as I dislike the DPT case, I would prefer this over putting into userland. The main argument is that you want to see the possible deadlock before it actually happens. And therefore, yes. But didn't you want to push everything to userland? No. Didn't you want to push everything to userland? Do you want to push this into userland completely instead of having it in kernel? I'm not saying it would be cheaper, because it depends how many locking events you have per second, because this is all the thing you have to process in userland. So instead of making this processing in kernel, you would do it in userland. So you have still. It would be enabling it in production, you would say. Right.
I personally, I'm not sure. Like you cannot inline spin lock. That's, I don't think the production. Right, but like
like 10%, like 10x. And if we did this, kernel can like only 2x slow. Then that means more bug you can detect. That's where still valuable, I think.
I agree. I mean, I think, but
Getting hit by extra costs and the stuff that you're not interested in your particular debugging session. You just don't attach kprop, and then there is zero cost. Well, except for uninlining.
Hi, I have two questions, short ones. First one is, as you know, probably lockdep does not track individual locks, but rather lock classes.
I'm sorry, can you speak slowly that I can understand?
Okay, so lockdep does not track individual locks, but rather lock classes. How do you deal with this? Do you reuse the lock class abstraction from lockdep, or you have your own?
Sorry, please ask again one more time.
So lockdep, if you just give it a lock, it will not track each instance of lock unlock on that lock. It will track all of the
class
instances, like the entire class. So for example, if you have a struct that has a lock, all of the struct instances will will be the same lock class.
Yeah, you are right. Yeah.
Do you use? Do you have a mechanism like this?
Yeah, I use the kind of a class.
Okay.
Rather than each instance. Yeah, that way we can track the potential deadlock condition. That's why. Yeah.
And second question is, can you comment a bit on the performance overhead of lock depth versus depth?
For now, the overhead is more than lock depth. Yeah, I need to optimize that. Yeah, more. It has a more overhead. Yeah, I think the overhead will be increased as the amount of targets that interested in. Yes, they're gonna raise.
Have you considered using actual lock instances for tracking? Because those classes are a constant source of false positives for lock depth, which is not good. Have you considered not using lock classes, but instead doing dependency tracking on the individual lock object level?
You do have if you do it.
And
it's a unfortunate way for now. Yeah, but someday I was thinking of that, but I'm not sure it's feasible or.
There may be some ways, some bit matrices. Sorry, what?
I think you asked me because of the false positives to avoid, right?
Yes, and the memory is cheaper than maintainer time debugging all of the false positives and fixing.
I think it's proven as more makes sense than I can try, but now I still need to think.
Yeah, so another question here. Yeah, so you mentioned that this tool will not stop as lock depth stops after reporting one lock depth dependency issue, right? You will still keep going on and report more issues, right? So if you report an issue, would you blacklist it so that I will not see similar lock depth chain problem for subsequent issues?
Sorry, again, please.
Yeah. So this question is, you understand this question?
No, I didn't understand. Please repeat.
Yeah. So let's say you report an issue, you don't stop, you report other issues.
I said depth doesn't stop. Yeah.
Lock depth stops the issue, stops once after issue is reported.
Right.
But your tool depth would not stop that.
Yeah.
It will keep reporting other issues as well.
Right.
So when an issue is reported, would you again report the same issue again if it happens?
No.
So you blacklist that chain and the same issue would not be reported again.
Yeah, right, exactly.
Okay.
Yeah.
Okay, so that is good. Yeah. Fine.
Yeah. That manages the hash value of each identical issues. So yeah, they avoid to report same issues more than one times.
Okay, thank you. I think it will be last question. When I saw the depth, there is some aggressive mode in there. So what is the difference between the normal mode and aggressive mode?
Okay. Usually developer use general wait with the timeout specified because sometimes it's very hard to avoid hang if we are using general wait. So we sometimes specify timeout. So it doesn't cause deadlock issues, but it can create dependency problem. So even if it's not actual deadlock, but I wanted to report there is dependency issues, even if they are using timeout to avoid deadlock. That's why I named aggressive mode to report even timeout wait. That's different. Okay, I think it's over.
Yeah, we already over time. And thanks again for a great presentation, and thanks for everyone contribute to the discussion. And we have a break. Let's come back at 12 o'clock for our next presentation. Let's applause again for our speaker.
Thank you very much for attending.
그럴 거라고 생각을 했고. 근데 리더가 다음에 리더를 기다릴 수 있어요.
그쵸. 그쵸. 그 얘기한 거예요? 그거, 내가 알아들었으면 됐는데. 그것도 할 말 많은데. 고마워요.
charge here? Are you in charge here? How do I share I'll try it. Yeah, let me know. Let me know.
Just go to this page, and then just left to right. Turn this on, and that's it. Hello, everyone. Welcome back. We have our next presentation about user space assisted scheduling with Schedule QoS. And we have our presenter, Kias, and Vincent, John, Stephen in the room. Let's welcome our speaker.
Hello, everyone. My name is Kais Youssef. I work with the Pixel kernel team, like a lot of scheduler stuff. And like here, along with Vincent, Steve, and John, hopefully like you know a lot more than me. Hopefully give you like a little bit of a plan and like a roadmap of where we think we can hopefully finally get Schedule QoS implemented and what needs to be done. We're going to take a bit of a different approach this time. A lot of discussion has been in the past into like APIs, but it's really a small part of the problem. And there are many issues need to be addressed to really reach that point. So hopefully we'll highlight them all. First, a little bit of like background. So like Linux is very diverse, like have a lot of diverse users. Like it needs to support a lot of hardware, like from server to very small embedded systems. And you know, like in Android as well, you get these hybrid systems. And it needs to support a lot of workloads. And historically, like server market, like has been the major contributor. So like it has a little bit of throughput bias, like which I think has been getting better over time. But like interactivity is really becoming important, and a lot of people complaining about that. But balancing both is quite hard, and getting the different aspects of the workloads handled is really hard. And like it doesn't help that applications are like written really, like in my opinion, a bit of archaic way. Like they assume they're the only user of the systems. Like you get them spawning any threads based on CPUs, not being friendly to the fact that there could be another applications running. So like spawning that many threads is bad. And POSIX, unfortunately, hasn't been like revamped to describe like, hey, we really have different workloads, hardware, the world has moved on. How can people write applications better? It's quite hard. So hopefully we can fix all of that. And I do believe we can fix all of that with one scheduler. We don't really need like something else. But the scheduler needs a little bit of more information to do a smarter decision. And like the question here is like how we can get this more information. And that's what we will try to address. And like over here, we'll make a number of suggestions. So like we're really focusing here. We think that a Schedule QoS kind of a middleware library is going to be instrumental to fix this problem. So a lot of the suggestions here like will belong to that layer rather than in the kernel. Although like there are kernel issues that we need to address as well. And we'll come into that. So this is like just like a little bit of background of things in the past that has been discussed. So hopefully we'll take a more comprehensive approach this time. So the roadmap. So like in my view, like to really get like a proper QoS like framework to work, we need to solve a number of problems. Like the QoS plumbing framework is actually one aspect, and that has been had the focus historically on. But people forget that the wake-up path and the load balancer will play a key aspect. If you have a QoS and the load balancer does not react to honor this one, how you can do it? Like you'll fail immediately. So whatever you do. So I think I've been raising that, and we'll come into this like in a minute. But the adoption problem, like people keep complaining, if you're gonna basically introduce QoS, then do you have to rewrite the whole world? The answer is yes and no. So we'll get into that as well. So how we can fix this. There is issue with the default values, as I touched on, like historically, like it's been biased toward throughput. It's getting better, but getting the balance is quite hard. And I think we can introduce something to help like introduce some balancing. And I think in the past, like, I mean, yesterday, if people like have seen, there is a lot of PI issues has been coming. And if you introduce of this QS and then you don't have this generalized inheritance, how you can, you will reach a corner cases where like this fails over. So you need some generalized inheritance. So whatever QS you're adding will help you ensure you deal with these contentions. And there are access control problems to handle. Like you need to give the admin the power to basically say this application is allowed, not allowed to use a QS somehow. With that, starting with the first part is the plumbing. So people have always been focusing into the kernel interface. And in my opinion, kernel interface is really like not the problem needs to be looked at. We need to look higher up. So we need to look how we can describe applications portably and like scalably. So we don't care. I mean, if they give them information about the kernel, we lose that battle already. So we need to abstract that. And if you look in the industry, actually, there is already a solution out there. Like Apple is giving its users like a very simple API or QS classes where they can describe their workloads for years. And people seem to be very happy with that. At least in my experience, talking with people who write applications for Android and iOS, they told me like they're quite happy there. They get what they need. So like the simple solutions where thinking is fine is just like, hey, if it works for them, it should work for us. So it's not a problem like what interface to introduce. It's just basically, instead of focusing on what kernel needs to do, let's focus how we can describe application generically using that one, and then how we can map this through that middleware, like SCID-QS middleware, to the kernel. So abstract the problem for them and make it like a single point of like mapping, which is this middleware, and gives you the scheduler stuff. And we're going to talk about the mapping. But there are 4 classes over here. So like they propose user interactive, user initiated, utility, and background. So we'll go through them. First, like a little bit about the mapping. So we think we have almost everything we need over here to do the mapping of these classes to give you the effectiveness of what they mean. So like the runtime, to control the slice size, which is an EVDF, will control your deadline, and that's basically how we can get the latencies. Policy, I focused on normal and batch, but like wake-up preemption is a problem. So you don't want a background task to force a wake-up preemption most of the time. You can actually use batch to disable wake-up preemptions for things that are not important. I didn't discuss idle. I didn't put idle in the mix because it might be too strong of a hint, and starvation issues might be a problem, but I don't know. It's something maybe you can look at. uclam max to manage power management and thermal for things that are not important. I'm not using uclam min. I think it's quite hard to be portable in that sense we want. But there is a new element that's actually not there, the ramp-up multiplier, which is to help with DVFS performance. There is already a proposal on the list, and the way this works is basically you give a multiplier, and this will make like your DVFS response time gets a lot faster or slower, and that will help you. Okay, like dynamic voltage and frequency scaling. So like your frequency, like basically your CPU free governor will behave faster using SCID util, which is our default governor, so that you get like the performance requirements, like without having to be very exact using uclam min. So like how the mapping works. So like first, like a bit of like what each of these classes I think means. If you look in the Apple documentation, it's actually quite hard to parse. So I tried to narrow them to like very simple wordings, like user interactive, something basically needs immediate response. Initiated, it's like, hey, something important, a little bit of a delay is fine, but like, please make me run fast still. Utility is like a lightweight background task, which is basically like, yeah, I'm happy with long delays, but if you actually delay me for too long, something can be happening. I don't know, like for instance, like some networking activity, not networking, like file system related activity, like writing to disk or something, which maybe like is important for the user, but not too bad. And background basically says like, hey, I don't care about if I'm delayed for too long. I'm fine with that. And it's very important to stress like what's the default behavior for tasks that are actually spawned where we don't get QS. And that's really important aspect. So like I think everything by default should be running utility. one of the biggest problem we have is like to give latency or like any kind of QoS response. By default, currently today, everything is considered important. You really want to reduce the noise level of like the default tasks running. It makes you giving like some kind of guarantees a little bit easier. If you tell the scheduler, like assume everything by default is not important, and I will let you know when there is something important, and then there should be few, like generally speaking, like if you have 100 tasks, maybe like 10 of them are important, the rest is just noise. So if you can know that the rest are noise very safely and you tell the scheduler, then it's very easy to cause preemptions for these noisy tasks and just let these 10 tasks compete with each other. So like that will give you a better behavior. And with the mapping, it's like, I mean, this is only suggestions, to be honest. Like, it's not really like what I'm saying. We'll need to do more experiments, like especially with the runtime. I know the others are fine because I've tried them. But like with user interactive, we can, I mean, let's start from the background. If we make background really have a very long slice, 20 millisecond, then utility 16, then user initiated and user interactive can still ask for a longer time slice, like 10 and 8. So like they get a longer runtime, but still be able to preempt the other classes using EEVDF, which I think what Peter had in mind when he was designing this interface. But for it to work, like you really need to make sure everything by default have a long deadline. Then you can easily give like the important task a longer slice and a shorter deadline where they can preempt the other tasks and get the latency that most people are after. And with the policy, like background and utility will be batched. So like you disable wake up preemption, you say like, hey, if you wake up and even if you are supposed to be running, keep the normal tasks, which are usually like important, finish their slice. And when they go to sleep, you're okay to basically run. And the ramp-up multiplier just to ensure that the DVFS response time is really fast, like for user interactive, because they need immediate response. So if you just happen to wake up and like it's small and starts running really busy, like becomes bursty, so you want the frequency to really go higher in a very short period of time. You don't want it to take like a lot. And if you saw my talk last year, like about the black hole effect, the utilization signal by default, which what drives the frequency is really like by default doesn't work very well. But with this aspect, you can actually like, and actually like shipping with this stuff, like it's actually helps quite a lot. And there is another question to ask. It's like, generally, how interactive is interactive? Because like, I mean, if you want to be portable, like I think like, hey, some people might come, it's like, this is too much for me, or this is too little for me. And I would like us to really to have one thing that works in all systems. To handle this, I think it's really important maybe to ask applications to tell us what's the period they're working on. And I avoided to use the word deadline because people will think like it's a hard deadline, and I do think that's a hard problem to say. It's like if we say these tasks are part of something that's periodic, and the period is basically 16 millisecond, 30 millisecond, whatever. Like I'm using FPS here just to describe like as a potential like game, for instance. So if somebody wants 2040 hertz, which means the deadline is 4 milliseconds, it's like you say like, ooh, probably with the mapping, I need to be a lot more aggressive because these things need to really run ASAP. But if an application tells me like, hey, I'm actually part of something that operates on 30 hertz, which is like 33 milliseconds, I say like, hey, you're very easy, peanuts. You're probably like, with background, you can potentially like get something done. I mean, we don't want to dilute it that much. But you can actually do like, get this extra dimension of information to help us deal with the different requirements of application of how fast they perceive is fast enough. So if you need something that really needs very short deadline, just tell us the period we can do. And additionally, I think that has been discussed in the past, and I know that Vincent had ideas. We can pass this period to the scheduler. So it can do actually like more stuff outside of this user space. The scheduler can look and says like, hey, your period is like really short, and you are being runnable or running for this, maybe I'm gonna just boost you with your UCLAM, do whatever work just to help like give you better guarantees like that are very hard to do via mapping. So like you can use that information to basically do even better job like at the kernel level to basically give better meaning for what these like hints mean based on the runtime and period basically. The next one, I'm not sure if anybody has a question on this topic before I go.
So this is very much focused on normal, essentially scale normal. Why forgetting scale 5 ORR and scale deadline?
Because like from latency wise, like, I mean, we don't have the same DVFS latencies, like people who use RT, it preempts everything by default. And like DVFS usually is disabled. You just run at a constant frequency.
But that's not the case for deadline, right? Deadline has DVFS support. And also, I mean, when you're talking about runtime period, for me, it's one-to-one mapping to deadline.
You really want to run Chrome underneath your deadline scheduler?
I don't know,
mean,
but
you may not buy it, but like, well, the point is, this is more for like deadline and real time and stuff like that is very much good. It definitely has a use case. I mean, obviously, I spent my life basically helping work on it, but no, we're talking about normal root utilities. Like, you know, you boot up, you have X windows up, you might want to kick off a game. These are also real time also requires root privileges and such. This is all user space privileges that give hints.
The question was basically why I don't use real-time policy to describe the mapping, or why I'm not using QS for real-time.
For me, really, a runtime period, it's one-to-one mapping to what deadline actually asks you to provide, and then uses that to do the scheduling. But apart from this, I guess I was also wondering, so you're proposing a QoS interface, but then it's not really a general interface. It's a QoS interface for using normal scheduler. So it's kind of, you're saying you're doing like a general thing, but you're not.
Okay, like to be honest, like I don't know. So like you're saying you want QoS for real time.
QoS for the system as a whole. Then you can decide, I guess
to be
it would
honest,
be
like,
nice to have like a description, a high-level description as you propose, and then do the mapping using all the what the kernel can provide.
I can do, but to be honest, I'm not aware of the real-time problem, so that's a discussion we can have. But if somebody with real-time need a QoS, to be honest, you need to feed me some requirements. But I don't think there is any reason that cannot be extended to real-time. It's just my idea with real-time, or you're using deadline, you're already like, it is a QoS in its own right, but it's just very hard to use a QoS because like here, like we care about multi-applications tenants. You have application E, A, B, and C need to live together. With RT, I'm not sure how you can generalize this without doing like global priority, for instance, mapping. Like,
no, yeah.
I don't know what's the priority like for each application needs to be right.
Priority, I completely agree. With deadline, I don't. Because deadline, it's essentially, you can do partition. I mean, that's essentially what it does.
But doesn't deadline have like a little more strict? Like we're not being strict here. Remember, this is all very not even real time. It's more soft real time. It's just performance, you know, quality of service. It's
yeah, it can,
deadline's a little bit.
It is strict.
Yeah, you can do it with deadline, but I'm like, I think it'd be much more complex in trying to get deadline working because deadline has strict numbers, where we don't. This is more of a. These are hints. They're not requirements.
Yeah, I get that. What I'm saying is that if you are, I guess here we are talking about the future, and saying deadline is strict now, it's kind of I feel we can miss an opportunity to make it less stricter, and then end up with a better overall solution.
How about we stop saying deadline and say bandwidth scheduler?
Yeah, I agree.
Yeah, I think because I think the throwing is when you say deadline. To me, when you say deadline scheduler, I'm thinking you know EDF or and
yes, strict, I agree.
Strict deadline. So if you say bandwidth scheduler, like if we had like a bandwidth scheduler that is more open, free, I mean that we do have, and start utilizing that, that could come later. I mean, once I guess also I'm not sure if you mentioned this or not about how this is kind of comes from Apple, right? Like
so the higher level interface, yeah.
Yeah, the high level interface is actually something that Apple uses and is very, what from my understanding is very successful using like this interface. So we're kind of looking at, well, if it's successful with Apple, let's try to do something similar.
No, and I fully agree. I mean, I really like the approach. I'm not saying the approach. I really like what you're trying to do. I'm just saying that bounding us from the start to just use one of the classes and policies that the kernel has to offer.
I think that's what people are complaining about. So I don't think there is anything inherent in that prevent us to use it to basically do mapping for RT and deadline. If there is, please let us know. But to be honest, it's not a focus I'm aware people are having. So like, how do you do QoS for these classes?
In these two examples, we are using normal mainly because that's what is used right now in Android and in a lot of embedded device. But because it's mainly a mapping, I would say nothing could prevent someone to say, okay, for my system, that should not be normal, but but deadline scheduler. It's just, we are trying to map some user interface, and right now for us, sched normal is enough, and prevent any kind of problem. But,
Okay,
I mean,
let's go ahead. Sorry, I didn't want to
Yeah,
take too much
but
time.
the laptop is locked. Can you help me unlock it, please? Yeah. Can you please unlock the laptop? Yeah, okay.
Oh, this is LPC.
While the laptop is unlocking, can I ask a small question? As
Yeah.
if this is like all normal user space and application are expected to declare the spirit, how is it protected from like even the typically, like an mobile device fashion where application developers want their application to be the best in terms of performance and everyone will declare I need like user interactive. Does the system protect from it somehow?
Well, that's where the final part is the access control, where to be honest, like you'll have, if you want to give this to application, you want to trust them. But like as an admin, if you find somebody abusing it, you just need some access control to say like, hey, ignore this application's request. And like we'll come to the adoption part, which to be honest, like I'm trying to propose a zero API like adoption part. So that's going to solve the problems. Like maybe the application doesn't have to tell you this. Maybe you can specify it, but we'll come to this. So the second part is like, I think that's a terminology from Peter. I've seen the multimodal, but it's basically like at the moment, like when we have the wake up path, we more or less have four different paths we take, like three. It's like based on load and energy, like load and NUMA, and like core scheduling. It's missing any notion of latency first, so we need the wake up path to basically do a global search for that's missing in EVDF today. It's like when you wake up, you'll basically distribute and load, but that's not the best choice for latency. At the same time, you probably want load, energy, latency, and whatever else requirement, because I've seen people talking about the wake up path. They need best path based on memory, which is kind of normal it is, but the cache aware scheduling discussion tells you they need more. So we really need to unify these decision tree to be really done in a hierarchical manner, unified somehow, which I think something Vincent has been trying to at least slowly works toward. And it's very important that the load balancer and the wake up path use the exact same functions, because whatever you do at the wake up path, you need to do at the load balancer. It's like if you give latency guarantees, or kind of honor latency at the wake up, but then it's inevitable you'll end up with overcommit situation. And I've seen that, it's just like you have two CPUs and you have 4 tasks waking up. It's like, yeah, whenever another CPU can able to run sooner, you need the load balancer to immediately do. And that's why the push load balance becomes more important, to get this kind of reaction time to be done faster. But you need them to do the same decision. You don't want load balancer to be only based on load, which is what it is today. And it already breaks ES, because ES doesn't do based on energy, which I think is missing. And that's basically kind of what started this whole push load balancer discussion, because I was trying to do something based on power, and then push load balancer became more obvious. And this discussion led to even more, makes us think it's really the right thing to do. So I think that's basically what I've said just now. It's not all about load. We need to do more. And so what we can do, and I think here, Vincent has been trying to really address some of these issues, so I'll give him.
Yeah, so I can quickly speak about. So we know that we have a number of things that can be done inside the kernel. So typically what we have discussed during the microconf yesterday morning about, so the one thing that we have noticed is that the periodic load balance that we are using in sched normal right now working well in some situation, but it's not enough when we want to be interactive. And mainly because it's too big, mainly because it's based on I'm one CPU and I'm looking what's going on the other CPU, but not really about if there is any task that need to be pushed in priority or pulled in priority in this case. It's not really scalable. On the other side, we know that the deadline and the RT scheduler are doing some per task push algorithm. So what we would like to add is to add a per task periodic load balance, or mainly have a per task push callback mechanism in the first scheduler, which means that regularly from time to time we will look at when a task move from running to runnable state to see if we should take this opportunity to move that to another CPU. Maybe because it has been preempted by a shorter slice, but it still have a shorter slice than other tasks on another CPU, so we can migrate that to make it run quicker or faster. So that's something that would help in this global task placement that will fill some hole that we have with the current load balancing mechanism. So and for that also we need to use the same select function. So right now we have the select function at wake up. We have the periodic load balance that is doing something similar, but not exactly the same as the wake up. So sometimes we have some kind of conflicting. So where in this case, we'd like to always use the same policy and the same algorithm. So we'll have a consistent mechanism across all the runtime period of the task. The shorter slice run first. So that's something that we have right now when a task wake up on a CPU and have the shorter slice, it will preempt the current running task. But what we don't have yet is that this slice duration is not taking account to select the CPU. It's only once you're on a CPU, you will preempt. And what we would like to add is also that if you have a short slice, in addition to looking for an idle CPU, you should also, or if you don't have any idle CPU, you should try to find a CPU with a longer slice duration for the running task, so you can preempt that and run quickly instead of being stacked on top of another shorter slice. Instead of stacking the short slice task, you will try to spread them to run first because they are short. And if they start to run more than their short slice, they will be preempted and they will be put back on the waiting list anyway. So that's something that helps to keep fair because that's something we don't want to break, but also that help to this task that need to run short for a short duration quickly, they can preempt everybody and run first. And there we have another number of things that we'd like to improve. It's to get the user estimate for the per task utilization. Right now, the task utilization, we have a entity load tracking inside the kernel. We are also trying to estimate what will be the highest utilization of the of a task. But with the scale attribute, the user space is able to set the slice, so the runtime duration, and it can also set a deadline, which gives us a CPU bandwidth for the CFS task. So you can directly jump to the right frequency point or compute capacity point without trying to estimate. So that will be a way to, instead of estimating what will be the utilization, just to get the value from the user space. So that's something also that will help to run faster and to make sure that to meet the deadline that you have in mind. And the last point, it's also profiling. So yeah, the tasks right now in the scheduler are assumed to be all the same, but we know that some tasks come CPU bonded, others are memory bonded or IO bonded, and the profile and the behavior, depending on your CPU, will not be the same. So we'd like to track that to have a better estimate of the utilization of the CPU, which is typically having a memory bonded on a big CPU running at highest frequency. It's just adding more stall cycle on your CPU, whereas you can run on a smaller CPU with the same performance, memory performance effect. So that's a number of things that will be useful for the QoS, in fact. That's why we think we need this user space interface that will apply to what user space would like. And then the goal is to map that to the kernel interface that we have right now.
Yeah, I think the TLDR is like we need the unified path, and then we can do even smarter things once we have this refactoring being done. So the next problem is the adoption issue. So like I think that's the trickiest one. It's like asking everyone to move on to the new to the latest and the greatest is quite hard. And like from Android perspective, we've seen that like we give them user interfaces, but to see in the wild actually people using stuff, it takes a very long lead time. And then like things, I mean, if you have an issue, like if you want to fix it and wait for it to be propagating, that's a very long time. And like I've put here 12 to 18 months, that's actually a best case. Like you're talking about like 2 years, 3 years actually between introducing something and seeing actually being there out and about. So it's very slow. And I think we can do better. So like, I have this idea of basically zero API adoption. We can create a mechanism where you can describe this QS using some configuration file, like config-based hinting, I call it. And it's basically very simple. You just say like, hey, for this application, it's like over here, like for instance, like I used Chrome. You can say like, I mean, you can have a version notation where 0 means I don't care. You can specify the period, like what tasks and what's the role. Like we can use netlink. We already have a netlink where it tells us a new task was forked or it changed its name. So like it's very easy to create a listener in the user space that can listen to these creations of these tasks and ensure they belong to the binary described over here. And then you can do the tagging basically based on that. So like you don't really need to write APIs or like ask anybody to ship with what you need, which hopefully will fix this adoption problem, or at least make it significantly less of a problem that like, hey, you can just roll things out immediately, just like get that SkidQS library, which will do this parsing, give it a file of the application you need. I mean, the developers or like somebody who's interested, they still have to profile this application, identify these roles, so we cannot fix that. Although like you see them as machine learning, if somebody wants to create machine learning to basically create this file based on whatever they think is fine, it's up to them. But we don't care. It's basically like we give you the mechanism to do tagging without APIs. So like you can actually opt in and be smart, like easily. And I think it fixes more problem as well. So like even for us in the kernel level, when I introduce new APIs, it makes experimenting easier and worth working about like, hey, we have this idea, is it gonna work? It's not. It's very easy like to have like iterative process where you can do things around. So like it really like fixes the worry from our kernel side. If we have like a new hint or a new addition scheduler that can improve this mapping, does it work? Does it not work? Does it scale? Does it not scale? It's very easy to do experiments because you don't have to beg someone to basically use the new API and tell you what to do. So I'd really love to able to make this completely zero API so that we can basically get the world rolling very easily. And hopefully people, even as an application developer, like maybe you can find this easier to ship with rather than hard code it into your application. So you can update this independently. But like, I mean, I'm not sure if it's enough and we can get there. Like something like the period, for instance, like with this config-based is statically defined, but you can have a game that you can go to the option and change the FPS to whatever value. So like, should we give them an API to let us know this changed? Or should we ask the user, like you modified, like whatever is the period, default period for this application? Maybe you should like change your config file and update it. I don't know what's the right answer. So we might run into corner cases that we still need to give people some APIs, but I hope we can reduce them significantly. And by default, we can still like ship something that people can use and get meaningful output. It's just a question. You can potentially be smarter if the application opts in, but my goal to try to basically reach that zero API, but I'm not sure how difficult it is. We need to really deploy this in a lot of use cases and see what people tell us. Any questions on that part? Yeah.
But I think this was mentioned before, and I'll try to ask it maybe a little differently. So you've mentioned that some of the APIs that you're working towards, you've seen be successful in the Apple ecosystem. And as you're reading through this, like I've got a game and I have a higher FPS now. And so I want to be able to make sure things get done a little more quickly so that the updates happen in time for the next frame. But what is my motivation as the game developer to not just pick that faster period and then not do anything else? Because it's less code, it's less work, it's less impact to me, because as the game developer, I might not have the system in mind, which is what I would need to have for typically when we're talking about QoS, whether it's deadline or real time, we're usually talking about a systematic property, right? A systematic property. So how do we get the application developers to have a systematic mindset?
Yeah, that's a good question. To be honest, I don't know. I think we just need to like help people understand the problem better, because like at least with this config based, if they do something bad as a user, you can say, like, for instance, you care about battery life. If they did something like daft and they basically put the period always 240 just to guarantee you always don't lose an FPS, and you say like, hey, I'm running this on a laptop and my battery is shit, so what I'm gonna do, just you can go to there and like, hey, like fix it. So you don't rely on them to fix it. So, and I don't know, I think awareness is the only thing. Just basically help people understand what's the right thing to do, educate both of the user and developer how to debug these problems, identify them, and know what to look for. So I don't see any other alternatives other than awareness.
A lot of these QoS like hints that the application's giving is really amongst their own threads. And so they're prioritizing the important threads that they have versus the unimportant threads that they have. They're not necessarily doing it within the scope of the full system because that the system administrator is going to be in control of. Okay, and then these policies, the idea of having configs that can override even what the application said allows the system administrator to say, oh, well, we know this application just gives us the wrong thing. So like, let us override that config as well. So we can have like per task overrides as well as general system, so there's kind of layers to it, but.
Yeah, so this is where the access controls comes in. If you just want to ban an application of doing something, if you have no control. But hopefully with this config base, you actually have control. So it's not in the developer's hand only.
I think it's a really good answer to say that the system that we need the application developer to care about is the scope of their application. If that's a true statement, then they're motivated to make trade-offs within their own app. And that makes a lot of sense.
Yeah. So I think it will simplify the problem space from adoption and for us kernel, because like we always think we need SCADA-QS, but like what's the right kernel interface? But if we confine the mapping to this and the adoption to config-based, this means there is less APIs and binaries who's using something. There is only one binary using stuff, which hopefully we control.
Yeah, I was wondering if you had sort of done an inventory of the other mechanisms as ways of actually communicating this information to the kernel, because there's stuff in /proc, there's, set scheduler and whatever it is. I'm just wondering, because you're proposing netlink, I mean, is there sort of a precedent of actually using that for conveying that sort of information down? Or maybe would it be more appropriate to have something under /proc, like PID specific, or?
I don't know, but the netlink, because it gives you an event, so like your listener is very lightweight. It's like you are told when there is something happening. So it's like kind of a callback. So you don't have, I mean, your user space will be very efficient, but if you want to pull on Procafest or something, that will be like more intensive to implement.
Are you asking like if the application to use the proc interface, or, I mean, I think the idea is to abstract, like the quality of service will probably have a library that the application just says, here's how I'm going to perform. And then the library is going to do, if there's Procafest interface or whatever, we're trying to abstract the kernel from the application having to know what the kernel has to do. So we could have so if you have a library that says these are the way my threads and my things behave, you just say, here's my latency sensitive thread, here's my background thread, my garbage collection thread, and you basically prioritize, and you just make a config that says this is the way this application behaves. Then we could have this library, if a new feature happens in the kernel, that hands it to let the library do all the work. We're trying to abstract that out from the application.
Okay, yeah, I can get that. I get that's sort of a reasonable way to approach it. But sometimes people tend to sort of say, oh, what does the kernel interface do? I'll go straight to that and sort of go around the libraries. So,
well, that's what strace and ftrace and all that's for.
Okay. Yeah, so like, I don't think we'll finish the slides, but this is the last important point. The rest maybe you can read offline, it's fine. It's the default values. It's actually very, like I see people tripping this quite a lot. It's like the default values of the scheduler are really biased toward the throughput. I think we've got better, but I think every time we change something, you hit another problem. So like, I think here comes to like Steve has been talking about like having this governor, and this is basically a variation of it. You don't need a governor to give you different scheduler. But we need a knob runtime that changes this default behavior. So like if you throughput constant, like focused, like for instance, if we're gonna unify the wake up path, we'll make it very expensive for wake up. But we can use Kit features to disable all of these for people who need throughput. And for interactive as well, like you need different set of default values. So I think people need to be wary that, like by default, the scheduler like have some default values that will hurt like your throughput or your interactive, and sometimes they are mutually exclusive. Like for example, for interactive system, I really think that chart tech is very important to have in. You need, especially with eVDF, having precise time slices to help you get the like see the meaningfulness between these different like aspects of like slice request being honored as much as it can. So like once the slice finished, it finished and the next one runs is really important. If it's disabled, you will basically, your preemption points are kind of chaotic. It depends on your tech. And I think I tried to post on the list how people have sometimes 4 millisecond tech accidentally, which is really bad for latencies. Load balancer has another stuff, like the load balancer has like backoff mechanism, which I think needs to be protected by Skit feature and disabled by default for interactive systems, but for throughput probably is very important. And the default slice size as well is really makes a difference. Like throughput, they need a long slice size, but like interactive system, like the 3 current millisecond is good for them. And for QS based, like I think we really need like a different things to describe it, because for QS to be really effective, as I was trying to say, it's really important that we reduce the noise level by default. But this means the performance going to be really, really crap. And we really need people to tell us like what's important and what's not. If they don't, everybody's going to be bad. But if we have this config based on and people tell us what's important, what's not, this is safe to do. Because like, hey, I'm going to give you the latency you want and everything you need by just basically just like write a config file for the application you care about and get your performance issues solved without sacrificing the overall system health. Like the whole like performance, power, and thermal all will be fine, like even in a laptop environment, because we know what's important and what's not. But the sacrifice with the QS based, like the configuration over here or the default values is like they will force bad performance by default to make it easier to give you good performance for the things that matters. But I mean, that's option, but like it's very important for people like who try generally to look at these problems that the default values of the scheduler, like you can charge them with debug FSF already today. So if you have issues, they need to be tweaked for different use cases. And that's really important. And like, I think abstracting this with a knob is very important so that at least we can hide it, like as maintainers or people working the scheduler, hide the higher level behavior you want. So you don't have to have expert knowledge about these default values. So we tweak them for you based on the performance you need. I could think only of these 3 classes that are required, but if there is more, please let us know so we can look at them. But to see the effectiveness of the whole overall approach, it's really important to consider like what's the default values and the scheduler level. Otherwise, you will see things falling over here and there. Any questions here?
So at Qualcomm, we've just started open sourcing something we've created, which uses a lot of the interfaces you talked about here. We call it User Resource Manager. And we're basically looking at C groups, clamps, controlling CPU frac, scheduling policies, and all of that. There's a classifier engine that doesn't need to be part of the build, the binary, but that can detect use cases and apply the config fragments as you were pointing out, appropriate config fragments for a multi-camera use case or audio paths and whatnot. It could be something that you could take a look at as a beginning for this implementation.
Yeah, that's great to know. Thank you.
We have about 1 minute.
Yeah, not sure if people have questions, you can take it. I mean, the last two points, like probably like performance inheritance, John has been really doing a great job talking about this. So I think the biggest things to highlight here is that we need proxy execution its own will fix the pie at the kernel level. We need user space to obtain. And I've been like having these discussions yesterday in the tool chains and talking with people, because without this generalized inheritance being in the user space, in spite of fixed all the other problems, you will still see corner cases where things fail. So like where I think real-time false has been complaining this about a lot. So like you will still misframe and say like, hey, it's not the QS framework is not working, but like there are really different bugs that you need to look at, including this one. So for all of this to be effective. So like each element will add an extra improvements, but in its own, it's not enough. You need everything to make sure that you're fine. And finally, access control, just very quickly. So you want the admin to say, like, for instance, like in Android, you have foreground, background, to say like, hey, for foreground, it's okay to have user interactive, but if it's background, ignore that request because it doesn't make any sense for something that I classify background. I mean, I don't know what the access control is going to look like. So that's the area that I need to work more on, like how to do it in the kernel level upstream. It's quite hard. But this is really important for this to be effective as well, to protect against abuse and to basically give this hierarchy of like control and deciding really what's need to happen across the system. And that's it.
So next we have like Dylan and Weinan talk about iSFrame for ARM64 reliable stack trace. Please join me. Give applause for our speakers.
So yeah, my name is Dylan. This is Weinan. We work on Live Patch at Google, and we're here to talk about a proposal for a reliable stack trace for ARM64. I advance the slides. Oh, there we go. So a lot of this talk is going to be sort of to contextualize what we're working on and why it's important. And then there's a lot of work that's already been done by people other than us. And so we kind of want to outline that. And then finally, we'll kind of describe the solution in addition to that we're proposing. So what actually is a stack trace? It's basically a record of functions recovered from a task's call stack that describes, in a way, the code path that was running at that point in time. So we typically see this as a human-readable format, and it usually comes with other diagnostic information. But it's a tool for reconstructing the code path for various profiling, debugging purposes. So sort of the conventional way a stack trace is created is we start at the top of the stack, and we use the frame pointer register that's saved to the stack as basically a linked list that lets us walk back up the stack to reconstruct this stack trace. And then at each stack frame, we grab the return address. It's also saved to the stack, and that's how we correlate what function corresponds to each stack frame. Unfortunately, sometimes a stack trace is not reliable. I wouldn't take these diagrams super literally. I think any of these tasks would probably barf if they had these stacks. But this is kind of the mode that I want to think about, where the stack trace has incomplete information. We maybe don't finish the stack trace before we exit, or the function data is sort of incorrect, or we have duplicates. And more later on how this actually can happen. So why is a reliable stack trace so important? There's a number of different debugging and profiling applications that are sort of useful in a human readable way. And so the usefulness of these stack traces are sort of diminished when we don't know if it's reliable or not. We can't rely on useful output. And then on top of this, sort of the angle that we're coming at this from is LivePatch relies on reliable stack trace. So LivePatch, to kind of go over what it actually is, it's a system for applying kernel fixes without rebooting. And it does this using the module system. We basically load a module containing replacement functions, and then the replacement functions are inserted into the control flow using the ftrace framework. And then we apply a per task consistency model to make sure that we've actually transitioned to the full patched state. And we need reliable stack trace to be able to do this. So a bit more detail about what is this consistency model. So like I said, it's per task. So individual tasks are transitioned to the patched state when they're confirmed to not actually be running any patched functions. And that way we know that the next time it calls that patched function, it'll be in the patched version and not the unpatched version. And the transition state only ends when everything is switched to the target state. And so you can sort of be in this liminal state where tasks are coalescing towards the patched state. To apply the consistency model, there's two methods that don't rely on stack trace. The first one is you wait for a task to go back out to user space, and you can sort of consider it patched at that point. Or you can have the patch sort of patch itself, so to speak. This is kind of useful for anything that doesn't ever exit to user space. But there isn't a universal solution for stuff like K-threads and things that have custom loop logic. And so how does reliable stack trace come into play? Well, sort of the third and by far most effective method of applying the consistency model is we say, for any sleeping task, we check the stack of that task, and if it doesn't have any patched functions in the stack, then we're able to sort of mark that task as complete. And this works really well. I think usually the patch sort of is done after one pass a lot of times. And if not, you just sort of do another pass a little bit later, and the patch will be complete. And because of the complications introduced by K-threads, any architecture that doesn't actually implement this have reliable stack trace option, it isn't really supported officially by LivePatch. So what does it mean to actually provide a reliable stack trace? Well, there's a number of components. The first one is actually identifying that we've successfully unwound the entire stack before terminating. And so making sure that we actually, when we finish unwinding, we actually end at a spot where we expect, and that the location of that stack frame matches what we would expect for that task. And then finally, that the actual unwinder doesn't exit with an error, that everything sort of looks correct and doesn't have an error exit case. On top of this, we need to correctly handle interrupts and exceptions. This is kind of a unique case because the calling convention normally sort of provides certain guarantees about where the frame pointer and the return address are going to be on the stack. But in the middle of the function's execution or in the prologue or the epilogue, it's way more difficult to reason about what the stack actually looks like and what information is going to be there. So the frame pointer can be unreliable sometimes. The return address may be in a general purpose register. And so it's a little bit tricky to sort of hit that exception boundary and make sure we can continue unwinding past that. Another consideration is ftrace and kprobe trampolines can overwrite the return address to go somewhere else first before continuing to return back up the frame to the next frame. And thankfully, sort of a problem comes with a pre-defined solution. There's an API for correctly translating back to the original return address. And so if you're implementing an unwinder and you want to make sure it's reliable, you just have to know that this is a thing that you need to take care of. But it's sort of it's an already solved problem, so that's nice. And then link register unreliability. So during setup and teardown, the actual link register value can match what's already been saved to the stack, or it could be actually the only spot where the return address is. And so there's sort of a chance that we can double count a function by looking at both the link register and what's on the stack. So how does x86 do this? Well, in x86, we have this thing called the ORC unwinder. It provides reliable stack traces. And the way it does this is at build time, obj_tool, which runs at build time, it generates a mapping from a PC address in a section table to the stack metadata for that PC address. And so you basically can get a stack offset you can use to calculate the actual address of the next frame without looking at the frame pointer itself. So this is sort of an off-band method of unwinding the stack. And it's reliable. So there's a couple of benefits to this. You can end up disabling frame pointers completely, and so you get an extra register. So that's a big performance benefit. And because of the sort of build time analysis that obj_tool does, you can correctly unwind across exception boundaries, because for any given PC value, you can actually take into account any nuances in the offset of the next saved return address. But the big problem here is obj_tool isn't supported for ARM64. So we can't generate ORC unwind tables on ARM. So in the past, there was an RFC proposed for ARM64 to basically add the support to obj_tool so we could generate ORC tables for ARM64. So this is Madhavan proposed this. And the idea was that it was not going to do as heavy duty validation in obj_tool at build time, but it would enable this sort of dynamic frame pointer validation where it would compare the frame pointer recovered from the stack with the calculated frame pointer from the ORC data. And if they matched, then we considered it still reliable and it would continue unwinding. And then if they didn't match, then we consider that stack unreliable. And so to implement this, this is maybe a little bit of a tangent, but it was a pretty substantial amount of reorganization of the code. Basically, a lot of ObjTool code had to be sort of refactored into architecture generic and architecture specific directories. And the same thing had to be done for the org code in the kernel space. So it was a pretty substantial patch series. And the feedback that this proposal got upstream was that it wasn't really desirable for ARM64 to support ObjTool because of the reverse engineering of the control flow that it does. And so there's maybe certain edge cases that ObjTool won't be able to correctly handle, and that as code generation changes in the tool chain, we need to sort of maintain those changes in ObjTool, and that kind of makes the solution a little bit brittle. And so the consensus was kind of that something that used data directly produced by the compiler was preferred. And this kind of aligned with other feedback about ObjTool for ARM64 in past LPC events. And so S-Frame was kind of proposed as this alternative solution. More on that later. But now ARM64 does actually support this config option for reliable stack trace. So how does it actually do that? In 6.12, Mark Rutland landed a patch series that adds this concept of a meta frame record to identify these sort of key points in the stack. And so the two sort of key points that you would think about are exception boundaries and the final frame in the stack. And these are sort of the two spots that are still a little bit, that were a little bit not quite handled for the ARM64 unwind. So the way this worked is you would have one stack frame type, stack frame meta type that would sort of be identify the PT regs saved to the stack at the exception boundary. And so the way this would kind of work is you would say, okay, my frame pointer and return address is sort of empty, so that indicates that there might be a meta frame record here. So we recover the meta frame type, which would be this meta frame PT regs. And then we know to look for the struct PT regs. And then so we recover this larger struct on the stack. And then from there, we can grab our saved frame pointer and PC value to continue unwinding. And then the other type was the final stack frame. So this is a little bit simpler. So here you see there's the final frame type here. And we identify that there's an empty return address and empty frame pointer in this meta stack frame record. And we know that we're done unwinding. And you can also double check this against the struct PT regs of the stack to make sure that that actual final frame is where it's supposed to be. And then the other thing that this patch series added was this idea of source tracking in the unwind. So you could sort of, when you see your debug output, you would have different signifiers for the location or the methodology for which that frame was recovered. And then on top of that, you have a possible second source that would track whether or not it was sort of passed through the fgraph or k-rep probes to recover the actual return address. And there was an additional L type to track when the link register was used to recover that PC. But this was removed because the link register isn't always live when the exception occurs, when an exception occurs. And so linked register unwinding was still unreliable. And so the way it was handled is you sort of skip over that frame and continue unwinding. And we sort of need to handle this at a later point in time to handle a reliable exception boundary unwind. And then a follow-up patch from Song, thank you, was to complete this reliable stack trace support without S-frame. And the way it does this is it detects the exception boundary using the previous infrastructure that was set up. And then if it sees that we're hitting an exception boundary, we mark that stack trace as unreliable. And so the idea is that instead of guaranteeing or attempting to guarantee that every stack trace is going to be reliable, we just say, well, the stack walk reliable function API will just report when it is and isn't reliable. And in practice, this actually works for live patch, or should work for live patch. I think we'll end up getting this into production. I think Meta already has this in production. It works for live patch because tasks aren't always in an exception. So the second pass, you can sort of complete the transition. But I would still consider this to be sort of a partial solution because we still aren't fully handling exception boundaries, and the this isn't, maybe this is a bit of hyperbole. There's a little bit of benefit to knowing that the stack trace is unreliable, but we still, the humans looking at a stack trace, knowing that it's unreliable, it isn't the same as actually getting the reliable stack trace. And so there's still kind of work to be done here to complete reliable stack trace. So that's where S-frame comes in as a solution that we're proposing. S-frame is sort of orc inspired. The idea is that the tool chain itself generates orc-like data in an S-frame section, which generates a sort of a two-level lookup structure, and it avoids re-engineering the binary. So what does the actual S-frame data look like? It provides basically the information necessary to recover the frame pointer and return address for any stack frame. And then as sort of an intermediary step, you get this canonical frame address that sort of represents kind of the stack pointer at that stack frame. So this is kind of what it looks like. You have a table of FDEs, and then individual rows sort of form their own tables for individual PCs within each function. I'll expand on that. So the first table is function descriptor entries. So it provides function metadata that you need to sort of identify a PC to a specific function. So you get the start address and the size of the function and the number of FREs within that function, and some other data. And then the FRE table for that function is what you use to get the complete data to recover that stack frame. And so sort of quickly how it would work is you identify what you would need to use as your base register value. It's either sort of the CFA stack pointer or the frame pointer, and then individual FRE entries will give you offsets of the next CFA from your base, and then offsets from the CFA to where you can recover the return address and frame pointer of the next frame. So trying to visualize this, if you're starting with your old CFA, you get your base register value. It's sort of hard to, to show both examples here, but this is like if you're using the previous CFA as your base for the next CFA, you take your CFA offset and you add that to get your next CFA value. And then usually the RA offset and FP offset are negative. So I guess you would really want this diagram to have an arrow points back down to recover the frame pointer and return address values to unwind. And then this slide maybe isn't super useful, but this is sort of a pseudocode implementation of that algorithm of you get your base register and then your frame pointer and return address offset, and you calculate what you need for the next frame.
And I'm Wayne, and I'm give a summary of the current experience solution status. And I like we all know that a frame pointer based unwinding approach is not reliable. So for unwinding a cross exception boundary, frame is just like oak unwinder. We annotate where the base register and its CFA offset in the exception boundary entries. So compiler can generate those entries for those pairs, and that's how we can generate we have the table for that, metadata for that for unwinder to unwind at those point at those pairs, and X-Frame actually support multiple architecture. According to the doc, the spec, it will support x86 64, ARC64, and S390X. But I think that is working in progress. And with that, so we can actually for the S-frame unwinder, I think we can actually reuse same S-frame unwind algorithm for a different architecture without the need to knowing deeply understand the other architecture specific behavior. And since this is generated by the compiler directly, so for one of the benefit is we don't need to run the object tool again to generate those unwind table. And I think another thing is it actually can complement with FP based frame pointer based approach. It can fall back to the frame pointer based approach if a frame unwinding encounter error. For example, like if there's no S-frame data for the function, it could be because you are unwinding out of tree kernel module which is built without those S-frame information. So yeah, for sure it is unreliable, but it is still able to unwind for that kind of case. So S-frame also can. There is at the same time there is a proposal that is proposed by Josh, James, and Stephen, and they are people trying to use S-frame unwinder to support the user space unwinding reliably. And it can do that because if we let the kernel access the S-frame data for the ELF section of the user space program, then it actually can continue to unwind the code stack for the user space program. And one of good thing is since this S-frame based, so even if the user space program disable saving the frame pointer on stack, they can still unwind the code stack. So okay. However, S-frame is currently only supported by GCC right now. There are LVN support ongoing at this time, and according to the discussion, some of the LVN folks, they have some question about the implementation of the S-Frame. And another thing is they also worry about there are several improvements going to upcoming improvement, and it may change the S-Frame format or spec. Yeah, so they are a little bit worried about that. But to both broader adoption S-Frame unwind, I think this tool chain support is essentially for this. Yeah, so yeah, we really hope this kind of problem can solve. Yeah, and finally, and there are, like I mentioned earlier, that there are ongoing improvement to the S-Frame. A numerous of improvement are anticipated, and for example, like right now S-Frame can only tracking the CFA by using the FP and SP register. People want to make it more flexible, and another thing is probably they want to provide a mark to mark where is the almost friends, so people can understand whether the stack trace is complete or not. And there are other improvements as well, like if I recall correctly, they want to improve the offset size, the handle the text size that is larger than 2 GB, something like that. So yeah, that's the current S-Frame unwinder and S-Frame support status. Yeah. Have any question?
So by reliable stack trace, the way I understand is the unwinder can still fail, but if it succeeds, it must produce the correct stack trace. Is this correct?
Huh? I'm sorry?
So by reliable stack trace, the unwinders can still say, I cannot unwind at this address because I don't have enough info.
Yeah, that's correct.
Okay.
So in this case, we consider this is not reliable. Yeah.
And you can still retry later for live patch. So there is a handful of long tail edge cases. For example, on x86, if the function needs to realign the stack, there is a few for a few instructions. The stack pointer needs to be spilled, and it cannot be unwound by current S-Frame format. So in that case, you might hit a non-unwindable region, and in that case, we need to fall back, or really, we need to retry.
Yeah, I think the main aim is to improve unwindability.
Yeah, right now we have no ARM64 reliable unwinder yet. Yeah.
It sounds like as long as you can retry it, it will work. Yes.
Yeah, and that's useful for live patch. But if you're sort of staring at a warning or a crash log, you'd like the unwind to be reliable, even if it hits an exception boundary, stuff like that.
Thanks for the talk. That was really interesting. So on ARM64, we're blessed with quite a few general purpose registers. And I know you mentioned earlier on about one of the motivations for x86 is to avoid the frame pointer entirely so that register can be reallocated. The motivation on ARM64, at least to me, is unclear that it's worth doing that. So in a world where we have frame pointers and S-Frame coexisting, what's your strategy? Is it that we would use S-Frame only for the exception case, or how do the two coexist, I suppose is what I'm asking.
So I had originally thought we would kind of solely use S-Frame for unwinding, but I had an interesting conversation with Mark Rutland last night where he was kind of envisioning an idea where, yeah, we only use it for exception boundary handling. So maybe and I guess the reason for doing that, I guess, is the unwind with the frame pointer is faster than doing this, because it ends up being sort of a binary search lookup to get the S-frame data. I almost wonder if we could have sort of the reverse model where we rely on the frame pointer initially, and we can maybe fall back to the S-frame data if we think that the frame pointer might be unreliable. I don't know. I still have to think about it more.
Thanks.
Question?
So I have a question. Do we have some insight into when S-frame v3 will be ready or finalized?
It's been posted for BNutils like yesterday.
Yeah.
It has to be committed, right?
Thank you. Have more questions? Okay, and let's give our speaker another round of applause. So we should have lunch ready outside, and we'll be back at the 3 o'clock.
From the committee.
We share the work.
Okay.
Upload the slides somewhere?
Right.
I can't find a way to upload my slides any place. Yes. Oh, here, yes.
And you go there, you can
Add my slides
do a
here.
little click.
And you will have them here. I don't need to come with my laptop. So I don't need to do anything. If I upload there, that's fine.
Right.
Come here and click. A pointer to show to the screen. Red dot. From here in case I want to show something. For the talking there maybe.
Agreed.
Yeah,
I like to do that as well.
Can change. Oh, yeah. One slide.
It's only one page.
The slide is quite small on the screen. Advertise my talk for tomorrow, just like a preview. Get more attention.
Talk with your talk.
Hi, can you guys hear me?
Yes, we can hear you. You want to join the
Yeah.
talk?
Too late, eh?
Let me bring
No, I did join the
mic.
talk.
Hi, Indu.
Hi. Yeah, I did join the talk. But at the time when I wanted to unmute, it didn't quite work. So I heard a comment around DRAP and the fact that you will not be able to stack walk in those few instructions when you are in the stack realignment code, right? So with the flexible topmost frames that he was talking about, with the representation that's being added in V3, you will be able to stack trace if the DRAP pattern is existing on x86. So I just wanted that to be cleared up, that we are handling that in SFrame V3. And that DRAP pattern actually is on x86 only at this time, right? The stack realignment pattern doesn't exist on AR64.
I think we only observed that on the x86. I think for the ARM64
Correct.
we didn't see this kind of pattern. Yeah.
Correct. Yeah.
Yeah. Hi, Indu.
Yeah. Thanks for watching.
Yeah, nice talk.
Well, I'm just looking forward to V3 to solve this. So thank you for clarifying.
Yeah, the patches are posted on the Binutils mailing list. So take a look. I posted them as RFC. I'm really looking for, people to take a closer look and see if they can provide me some feedback. So do take a look, please, on the Binutils mailing list.
So if I want to look at V3, not V2, which ones should I look at?
So there is a branch upstream too. So if first, I can send you a link later, but it's on Binutils mailing list. The patches are posted. And using those patches, you will at least be able to generate SFrame V3 sections.
Okay,
And
so
all the patches are posted in a branch on upstream binutils report too.
I can look at the binutils patches later. Thank you.
Yep.
Probes, K probes and the caret, caret probes and the F probe actually that change that are entries, return address. So that are there any issue to decode those entries?
I mean, I think
Yeah.
tracked internally.
Yeah,
Cover
yeah,
the
yeah.
Original. To be honest, I don't really know the details.
It works on the M64.
Yeah,
Oh.
I believe so.
Oh, that's nice.
It's definitely used. The API is used.
Yeah.
In
Yeah.
Thank you.
Thank you very much.
Yeah, it's unless the
How much benefit if they why they design nasty.
part that actually should be sorted.
How to modify process.
Thanks for
Nice to see you.
yeah.
How are you? Nice work.
Yeah, it's for servers, especially like cloud, you know, promises to cloud customers. Training workloads.
or anything? Or? I'll leave it to you to be introduced. And so, how much time do you want to leave at the end? I can give you. I'm supposed to give you these cards. That won't be shared anymore, right? Last one Saturday.
Hello. Yep. Thank you for coming to my talk after lunch. I hope it will be a little bit entertaining. My name is Ignat. I work for Cloudflare. I'm actually used to ask, like, do people here, is there anyone here who doesn't know about Cloudflare for the past 2 weeks? No? Yeah, so I will not tell what we do. Yeah, so I work on Linux at Cloudflare, and today we're going to revise TPMs and talk about how can we better utilize them. Okay, control. Is it, which control? Is it arrows, right? There we go. Is it backend? So everyone here knows what a TPM is? Who doesn't know? So yeah, just a quick recap. TPM is a small discrete chip present in all modern laptops and servers. Yeah, it's a discrete chip, so it's quite safe. It's passive, non-intrusive. It only responds to the command, so it doesn't like tap into your internals like Intel management agents, for example. So if you, it only does stuff if you ask it to do. But even though it's a huge foundation for platform integrity, authentication, and remote attestation, and it's any cryptographic chip, it can handle cryptographic keys, as chips should do, right? So this talk was partially inspired by James Bottomley presentation in 2024 on FOSDEM. I don't know if I saw him around. And he, at some point, he mentioned he one of the 3 people in the world who works on TPMs. So maybe some more, but like not a lot of people. But like these people are thinking about, when we talk about TPMs, we more think about like remote attestations. This is what most operating system use the TPM for, mostly Windows, and Linux is catching up, right? And like an enterprise security is like how to do remote attestations with TPM. But my presentation today is like, okay, if TPM is everywhere, why there is not a lot of open source software and even commercial software uses it? Like why my SSH server doesn't have support for TPM? It would be a perfect place to store my private key, or SSH client, for example, right? Why there is no support? So imagine you're not a kernel engineer, you're an application developer. Like what would it take you to use a TPM in your software, right? So this is my application, this is a TPM, and this is kind of my ideal worldview of how would I use a TPM, right? So like, yeah, TPM, do. Obviously, it's not that simple. Like I'm running on an operating system, I'm not talking to hardware directly, so I need an abstraction layer, and in Linux it's dev_tpm.0. But it's not only the thing I need. I also need a thing called resource manager, right? Because TPM are very low-powered devices that cannot handle requests from many applications at the same time, and modern operating systems are multitasking, so there may be many applications using. So you need like an entity who would serialize access to the TPM so it doesn't get confused. And obviously, to talk to that resource manager, you need some kind of, and it's a TPM library, so to implement that API. So yeah, so like, but your code is green, right? TPM is blue, and yellow is an operating system, and purple is like all your dependencies. So now let's zoom into resource manager. Well, traditionally, resource manager was a daemon, which was very confusing for developers, right? So yeah, I want to talk to a hardware device that is there, but if for some misconfig or bug in software, some service crashed on the machine, I cannot use the TPM. It's not a great deal. So luckily, kernel developers realize that, and now the resource manager is implemented in the kernel, right? So now you have /dev/tprm0 device, which is an internal resource manager. If that crashes, your system crashes, so it doesn't matter much. right? So like you will know. So it's less confusing at least. What about the TPM library? And like James likes to talk about this a lot. So there is an Intel TSS implementation, right? There is an IBM TSS standing for Trustware Software Stack. And confusingly, these implementations provide totally incompatible APIs. So you as an application developer need to decide which one you do support, but also, or if you want to support both, you need to write an abstraction layer. Or what if you want to distribute your application to a distro which doesn't provide one of these? So like there is a lot of questions, right? But also like if you write your stuff in Go, there is also a Go TPM library from Google, which because Go people, they don't like any extra C dependencies in their code, right? And I actually never checked the Rust ecosystem. I'm sure there is some kind of like TPM Rust crate somewhere, which also like goes into that bucket, right? Yeah, so like if you ever visit as an application developer this website, the TPM software GitHub, you'll see this diagram. So like, yeah, I mean, I want to use TPM and now I have to understand all this, right? Like which layer I need to connect and everything. So it's really, really, really confusing. And like my intuition, it confuses most developers and that's why they kind of like restrain themselves integrating the TPM support. But okay, even if you're persistent and you made it work, how do you distribute your code? So like, yeah, I developed an application that uses a TPM. Well, if I talk, this is like a standard bare bones Debian installation. And if I try to talk to the TPM, I get permission denied or the resource manager, because by default, all these two devices are owned by root, right? So like I need to have privileges. Confusingly, on Debian, if I install the TPM2 tools from Intel, now the TPM device will be owned by the TSS user, and the resource manager will be the TSS and TSS group, which is kind of like easier. So now my application needs to become part of the TSS group, right, to talk to the TPM. But then I need to properly package it from a Debian perspective to get into the group. And what if the group is not created? So if I write my code in Go, do I need to pull in TPM2 tools dependency, even if I don't use it, just to have the user created? So yeah, not really great. This brings us to Linux kernel key retention service, or aka keyrings or key store. People here familiar with this? Yeah, so key store actually provides a much simpler model to interact with cryptographic keys, right? So you have these applications, you have the Linux kernel, and you have roughly 3 system calls to care about, right? So, and applications can instantiate keys inside the kernel space, right? And originally, those keys were used for in-kernel encryption systems like dmcrypt, fscrypt, and crypto API. But also like other applications, if they have sufficient permissions, they can also use those keys as well. Right, so like you kind of like a kernel manages a key on the application's behalf, which becomes much more convenient. And like the structure of keyrings, you have keyrings, so like collection of keys that can contain other keyrings, and these keyrings can contain keys. So it's very similar to a file system structure, easy to understand, and keys and keyrings are proper kernel objects. They have associated ACLs, so you can kind of like design a very good fine-grained access control system for your keys or secrets. And the nice thing about it, like it all works for unprivileged applications. So it's just 3 system calls, any application can call them, right? So the question here is like, can we combine these two, the confusing technology? Can we enhance the functionality of Linux key store with TPMs? And Linux kernel really kind of has support for TPMs in the kernel key store. So keys can have different types, and one of the types is called a trusted key. So the trusted key was designed that you don't accidentally leak the key or a secret plain text into the user space. And the way how it works, so imagine like what process one has some key and it's wrapped in a blob, it's encrypted, right? So when that process instantiates that key in the key store, the kernel will use your TPM automatically to unwrap that key. So the key exists in plain text in the kernel space. But again, if you try to read it back, even if you have the permission, the kernel will automatically wrap it back. So you can never have the plain text key in user space, which is probably more secure, and only your machine with this TPM can only decrypt that key. So it's kind of cryptographically bound to your hardware, which is great. The limitation of it is, I think, it's kind of useful for cryptographic keys, but it's not quite useful for more generic credentials like tokens or, let's say, machine passwords, right? Because if your process cannot read the plain text, it cannot use it as a password for authentication somewhere. So it's kind of only limited to using that as a cryptographic key. And the only way you can use it, you can ask the kernel to encrypt and decrypt data with that key. There is another thing that I think is a problem with wrapped keys is the extra state. So the way how you would generate a wrapped key, so you take a random number generator, right? You generate your random key, and then you use the TPM to encrypt it, and you create this encrypted blob. And now, what do I want to say? The problem is, so with this approach, it's kind of secure, but it's still like the process or the application is still responsible for key management, right? So like, because the kernel itself does not have a persistent state when you reboot, so all your keys are gone. You have to reinstantiate them all the time, so you kind of like have to store that blob somewhere. And if you accidentally lose it, even though like it's secure, right? If you accidentally lose the blob, you can never decrypt your data anymore. So you have to like back it up and stuff. And like what about read-only systems? In my original submission that I posted more than a year ago, I mentioned stateless systems, but folks found that phrase ambiguous. So like, is there any ambiguity in the world stateless system? Or so like, because like when I say here read-only systems, but it oh
Can you hear me?
Yeah.
I'm not native speaker, English speaker, so for me it doesn't make sense. It doesn't matter. But maybe for native speakers there is a difference. Sorry.
Well, I mean, I want to explain. Like I mentioned here, read-only system, but actually any system that cannot persist state and can be like an ephemeral system like Linux running from pure RAM, right, without any persistent storage. Or you have a broken disk, which like happens all the time in harsh production environments. People wipe stuff, like we wipe servers all the time, and sometimes you just delete that and you cannot decrypt your data anymore.
So what you talked about wrapped keys and losing them, I think it's more about, I think what you are alluding to is basically maybe you can have derived key support, something like that.
Yeah, this is the whole point.
Yeah, but wrapped keys, it's about giving the user control. You can have derived keys as well. But yeah, there are pros and cons of both approaches, I would say.
Yeah. I'm just trying to kind of bring up to the problem that I'm trying to solve, and you're correct. It's kind of like wrapped keys are good, but they have some drawbacks as well, right? And another drawback is this, like, this all extra state I have to manage, because like, especially in production, you have many services and application, and each application wants a unique key. And then you have like, even though the keys itself are small, you have like this huge state of different blobs that you have to care about, right? So it's a little bit of a burden. what if we take another approach with derived keys? So like in the TPM, every TPM has a seed inside, which is non-extractable and tamper-proof, ideally, if your TPM manufacturer is good. So you can never get it. But you can use a KDF to derive stuff from that seed, right? And this all part of the TPM spec. So like you can be sure that your TPM has this functionality, so it's standardized, right? So what if we make application-specific keys by using that technology and just providing some unique application identifier? So like we can have the dimensionalities that we require for TPM-based keys, and like each application can now get their own key in a reproducible manner. And this process actually scales really well. So like you can derive like gazillions of keys for all your application, but that state is disposable, right? So you don't have to store it anywhere. As long as you have access to your TPM, you can recreate this set on each boot like reliably. So this was my proposal like more than a year ago to implement another key type called derived keys. I got some feedback. Some of it is not very actionable. So some of it actionable. Like I don't quite understand this feedback because the idea for that is not new, and I didn't invent it. I actually stole it from my mobile development past, where you can work with, if anyone works here with mobile ARM Trust Zone. So either open source, I used to work in proprietary ones like Qualcomm and Samsung. So every trust zone has this concept of hardware unique key where you can never get it, but you can derive keys from it. And like there are whole like systems and solutions built on top of it. And like your video probably is one of them. And we actually kind of use this approach already in Cloudflare for the past 9 years. So I wrote a tool for like less secure version of this approach, because I wrote a tool for that, and we kind of currently use similar approach, but we store the seed in the BIOS chip in UEFI, which is less secure, obviously, because it's not like a proper cryptographic hardware. And if you're interested in details, you can watch my YouTube presentation from 2017. At SRECon, exactly. I described, it kind of gives you a very interesting partner of managing keys on a big deployment of servers spread worldwide, but it's probably will also be applicable to large enterprise environments, managing laptops as well. So you can like revoke and rotate keys in a very interesting targeted manner. Since then, I made some changes that I wanted to present today, and it's like what I did, I also re-implemented the key duration approach. What I replaced is TPM-based HMAC operation with a TPM-based IS counter mode random number generator. It's kind of like the approach is much simpler now. It was much more calls to the TPM for a single derived key. James Bottomley here recently merged TPM encrypted sessions from the kernel, which is a cool security improvement, which I also integrated in my work. So if something is snooping on the bus between the CPU and the TPM, so you kind of like, they will not be able to grab the cryptographic material traveling there, because again, TPM is most of the time it's a separate chip. And it compiles as a module now, so it kind of gives you more flexibility as a user. If you don't want it, you can still compile it, but never load, so you don't have the burden. So how it works now, roughly, is like you have the TPM. A TPM has this operation called TPM2 create primary, and it accepts more parameters than there, but the most important is the algorithm that you want to use and this unique parameter, right? So we select IS counter mode, and as a unique parameter, you can use different properties of the calling process. So you can use UID, group ID, executable path file system. I'll present all the examples just now. So depending on the user, which parameters they choose, the values of these parameters are hashed, and they're used kind of as this unique value. So this is kind of like this derivation and personalization factor, which makes a key unique to a particular application. And once the operation is returned, you get the IS counter key. And this is, just to clarify, you don't get the key, you get a handle to the key. That key is still kind of resident on the TPM. You cannot get the plain text of that key. So to actually return something to the user, we construct a simple IS counter mode deterministic random number generator. So you just use this key to encrypt some zeros for the length of the user requested. So if user requested a 32-byte key, then you encrypt for 32-byte zeros, and then you get the final key secret as a crypto stream, and you return it to the user. Yeah, so here are some examples. So the first example, if you use just the UID, so you can use, I'm using the keyctl command line wrapper, but imagine it's just an application doing like the request key system call. So yeah, I'm requesting a key here. The mandatory parameter is size. So size 32 means I want a key with 32 bytes. And as a personalization factor, I want to use UID. So I get some key, right? And that just to show that the process is reproducible, I can delete that key, right? And I can re-request it again with same parameters. And you can now see that from a kernel's perspective, that key is different because the serial number of the key is different, so it kind of recreated it. But if you print it out, you get the same bytes, so you kind of like have this reproducibility. And like, for example, this key type will be common across the whole. This is like a user-specific key, so any application running under a particular user ID will be able to reproduce that key. So you can kind of like now slice and dice your key space depending on how you want, right? Yeah, and also wanted to show that it kind of like takes user ID into account. If I rerun that command as sudo, like as a different user, I get the different key. So yeah, in this case, like users cannot sniff keys from each other. To make it more specific, I also added a path parameter. So now the personalization factor is actually the calling executable path. Now, it was like a point of controversy on my original submission that like folks said that path is unreliable and we shouldn't use it. However, based on yesterday's presentations in the eBPF track, I saw some security approaches which take path into account, and the argument there is even though the path is not very reliable and you can kind of subvert the path to it's still how most users and administrators perceive their system. So like they will try to segregate key by particular path, right? I also have, and to show that it works, so like I specifically show the path of the executable. So like user bin keyctl gets one key, but if I copy that executable to a different path and we run it, I kind of get a different key, right? So now, yeah, this approach is a little bit less secure because you can imagine on a system with unprivileged user namespaces enabled, I can create user namespaces and mount namespace, do a bound mount, and I kind of can generate any path. So my trick up the sleeve to that, well, you can combine a user ID and path. And user ID here means not the user ID from the namespace, but user ID from the root namespace. So I think like this is kind of text you from unprivileged user name attack. So and it also shows that it's kind of like user can combine different derivations factor, personalization factor to get security compartmentalization they want, right? But yeah, in this case, if you're run this as true root, like if some privileged user tries to reproduce the same as in an user namespace as root, will still get the different key because their user ID in the root namespace will be different. For purists, if you really don't want to use pass, there is an option to use an inode number. I think so. Like I implemented two options, like an inode number and file system UUID. And I kind of think that you should use them together all the time, so you can cryptographically bind your key to a particular instance on the file system. This is very useful for, as again, read-only file systems. There is a now modern approach of building like immutable infrastructure where you pre-build the file system image, so you have kind of better control of the inode number, so you can like pre-create your file system in a way that like the executables you care about will always have static inode numbers and they will have reproducible keys. Probably not very useful for a regular installation where file system is different, right? And also it doesn't survive updates. If you actually like update your binary by deleting and putting a new one, you will get a different inode. So yeah, you will keep it different, but it's useful in some cases. And the last option I want to present is the code checksum. So here the TPM derived keys driver piggybacks on the existing IMA infrastructure. So if your kernel has IMA enabled, it doesn't even have to be enforced. It's just the support should be there. It will call into the IMA and hash your executable. So yeah, it will cryptographically bind the derived key to the executable code itself, right? And to show that it works, let me monkey patch the keyctl binary, my copy, right? So I know that the binary has an error string called bad message. I'll change one byte there to bad massage. It will still work, but if I rerun the same binary, now I get a different key because, yeah, the checksum changed and the key changed. Again, I think this approach is very secure, not very practical where you need to update things, right? So like if you change your binary code legitimately, you will have to care about that your key changes. Some of the actionable feedback I got from my original submission: what if the application needs to rotate the keys because of a suspected compromise? And that's a valid point. The way how it could be solved, I also introduced a free-form label for application. So applications do not have to have one key. They can use also a free-form label to have their own dimensionality of particular keys. And one of the dimensionality could be just version numbers. So you can label your keys as version 1, and if that gets compromised, you can rederive your key, a different key with label v2. So you can kind of like increment keys in this way. The other part is which was a valid point, is these mixing values are actually well known, right? So like I could go and check my file system UID, checksum of hash my executable, or yeah, check the inode number or pass, and I can just manually, if I have access to the TPM, right, I can manually feed those numbers through user space and get the same key. So I can steal the key from any application on the system. Most likely I need to have some privilege, but still, right? So how do you make sure that certain keys only can be generated by the kernel? So, and to solve this, I tried to use this approach. So we're using the TPM2 create primary command. And if you look at the structure of that command and other TPM commands, so they have like the following structure. There is a header. I put it in one box because it's not important. So there is a header in every TPM command. There is a handle area. There is an auth area. So there is a so-called sensitive area where sensitive information is passed, and it's kind of like on request and response. And there is a so-called public area where non-sensitive information is passed. So the nice thing, even if you use encrypted TPM sessions, not everything will be encrypted. So only sensitive area will be encrypted, right? So, but the nice thing about that, the unique value that we are using is in the public area. So what we can do is, instead of using SHA-256 of application-specific info directly in our driver, we concatenate it or prefix it with a string called kernel, right? And what we can do, we can also look for that string in the TPM driver if there is a command incoming from user space and kind of deny that, right? So we kind of reserve this, anything that does create primary with a unique value which starts with the kernel only to kernel space, and we just can deny user space doing that. So here's a practical example. So yeah, I patched the TPM driver, so like I can show that I can request primary with any unique value, so like there should be no impact to user space, but if I kind of try to request something with unique starting with a string called kernel, I get operation not permitted. So yeah, this is what I wanted to present. So the request for comments here. What else do you think is missing for easier adoption of TPMs from an application perspective? Put yourself in the developer's shoes, like what you're missing. Any other application mixins parameters to be implemented you would think useful, or any other use cases to be considered? The thing I'm not sure about, should we support better separation between generic secrets and non-exportable keys? Should I add a flag? So like in all these examples, I could read the key back, but maybe we can add support that if I really don't want the secret, but a cryptographic key, which you can never extract from the kernel, the driver could also support that. Yeah, and probably would be nice to piggyback on advanced TPM capabilities. So if I'm using these derived keys and they derive from the TPM, maybe for verifying systems would be nice to have a way to optionally piggyback on, let's say, what's it called, TPM credential activation to actually get a proof that that key was derived from a particular TPM. Yeah, and if you're interested in code, here is my branch with the work in progress thing. Thank you very much, and I'm happy to answer questions.
I just wanted to make one comment here. I think you referenced that Opti hardware unique key support. And all the derived, yes, we are using derived keys, like everything within Opti framework for secure storage and everything. We use derived keys. But the thing is, like the code base there, the Opti code base, we trust that. That is like the TCP.
Can everybody in the back hear this? Is this coming through from this mic? No. Okay.
Okay.
A lot of that, and use this too.
Okay.
Just don't throw it. Okay.
No. So the thing with Opti and the usage of derived keys there is because we want trust to be in there.
Mm-hmm.
It's a trusted execution environment, and we don't expect these malicious attacks that are easily possible. However, I think what James' point was, like when you expose this interface to the user space, that is like the attack vectors there, that is much larger. How you protect against those attack vectors, because now your system is owning, like it can reproduce the keys to the users, and it can be malicious user or it can be a real user. How do you protect against those kind of attacks? And you can do things. So it's most likely like with the wrapped keys, you give it to the user, like export it in a wrapped blob, where without that wrapped blob, the system is not able to do any decryption or encryption. So it's like, yeah, it can be usable with different threat models as well. But I'm not saying that your solution is not usable. I'm just trying to give you the broader picture where the comments are coming, like what is the threat model and whatnot. So in a particular threat model, surely this thing would work, but yeah, in another threat model, this might not work. But yeah, it's still a useful feature, I would say.
Yeah. I mean, and thank you for the comment. And I guess, yeah, it's not to replace wrapped keys. It's more like to complement. And maybe the focus here is even less on security. So like maybe the wrap keys are more secure in that sense, because you can never have plain text in user space at all. That's kind of like non-debate. The here is like ease of use and like adoption. So like I would probably never adopt a wrap key as an SSH private key, just because like SSH cannot talk to the kernel to do signing operations. But I probably could use this approach to derive my deterministic SSH, like server key, and have it. Like I'm thinking about, like I'm usually thinking about like home router, that like when you SSH into it, you always have a different key because it doesn't have any disk, or like it runs from ROM and it kind of regenerates it on every boot. And like at least with this approach, I can have a deterministic key for my home router, right? So.
I just wanted to quickly mention, in systemd we had added some infrastructure in the form of service credentials and system credentials, which are TPM bound, but they are not derived, right? Like you can actually provide your own secret, and we'll encrypt it, lock it against the TPM, lock it against a verified boot, and things like that. And you get the binary and you store it away wherever you want, and then you can come back and get later. I just want to mention this because that's our approach of making TPM more accessible to users, because they don't really have to think. They don't even know that there's TPM involved. For them, it's just an interface where they have an IPC interface, and where they just pass the data and get back some blob, and later they can pass that blob back and get the data back. So yeah, just want to mention this because it sounds very similar to this.
Yeah, I actually saw the service credential support in systemd. I didn't know it uses TPM. Actually, I thought it's some kind of software solution.
Yeah, and it's like actually hooked into everything in systemd, right? Like you can provision a system by just passing in a couple of encrypted credentials this way, and everything happens magically. And again, like it has the hookup to the verified boot stuff. So right, you can have your credentials that only unlock on if you run the right software and things like this. So yeah, what I don't really understand, why is this needs to be in the kernel? That's the question I have, right? Like because we do all the parameter encryption, things like this, also in user space.
Well, I mean, the point of kernel here is, this is like the second point. If like, what if I want to make a non-exportable key at all? So like, what if I want to, similar to wrap keys, never expose cryptographic material to user space and just use it like a soft HSM, which I think is more secure. And the second part is, I kind of trust the kernel doing this, like gathering this metadata, right? From a kernel context, I know the inode, I know the calling process, so I kind of like, well, you can do it with systemd. I can hear my colleagues screaming that like getting like something from proc is racy, and so.
I was going to say, I thought it would be quite useful to have the non-exportable keys to implement the SSH private keys kept in the kernel. So sure, it's not quite as good as keeping it in the TPM itself, but at least it's protected from user space, taking the keys.
Well, the SSH part is a little bit, requires more work, because if you want to keep the keys in the kernel, then the kernel needs to be able to do private key operation. And the only one possible now is RSA, and it's not very secure because it's an old port of libgcrypt, and it's subject to
didn't realize that. Yep.
So yeah, it's kind of like, I would also love to have that, and I keep having this discussion like everyone else on the crypto mailing says kernel should not do private operation. I think the kernel should do more secure and better private key operations.
Yep, I agree.
Yeah, there is one.
Thank you. This is more a comment than a question, because at the beginning of presentation you complained that not a lot of open source work is working on the TPM. So I think that I want to share with you information that Grab currently for few years have a support for TPM measurements, and also recently we just added the TPM support to store the keys for this decryption, and this support will be available in upcoming release, which I'll hope will be in a week or so. So this is just a comment for
yeah. And what I think, like I saw the tendency of TPM adoption in more like low-level operating system component. The kernel system D, it's not that like application developers jump into, like I'm writing this daemon and I want to encrypt like my communication with TPM. That's kind of like where I was getting it.
Cool. Okay, any last questions? Anybody remotely?
One last thing that I want to mention, like regarding the parameters that you're mixing in, the thing like from a system perspective that we think is the most useful one is actually C group, right? Like C group pass, because that generally identifies precisely the workload, right? Like because it contains the slice, the actual service that's doing this, and if you have containers, it can also goes all the way up to the root of the tree, right? So yeah, in system we actually have this logic as well for the credential stuff, that if a user, like an unprivileged user, wants to encrypt a credential, we mix in the C group pass and the user identity.
That's cool. Like that's good info. I also was thinking like there was a discussion yesterday about the pass instability, and like there was an approach to use like extended attributes as well. So maybe I'm thinking about these support. But yeah, C group is a good idea, I think.
And the other thing is you shouldn't use inode numbers or something like this, because they nowadays are not like they can be recycled too aggressively, right? So, but you can use the file handle stuff if you want that.
Yeah. I mean, I know it's like explicitly for read-only file systems where you don't create stuff.
Okay, that's all. Thank you.
Thank you.
Good discussion. Is this one working yet? Nope. Any audio out of this? Oh, there we go. Brian? So you got 40. I'll go through the slides. Leave the amount of time at the end there. Just
Wait for it officially. Okay, let's go ahead and get started. So I'm going to be talking to you today about how we do safety with Linux kernel, at least NVIDIA's idea for how we do that. This is a presentation I gave earlier this week at the Automotive Linux Summit. So, so this talk was kind of a late edition for plumbers. So bear with me for some of the slides. I'm going to keep it as interesting, as technical as possible, but a lot of these things were kind of written for a different audience. All right, what's the magic key? All right, really quickly, I'm not a safety expert, but a lot of people who work with are. I'm not the original creator of this concept. He's hiding somewhere in this room, or at least he gets a good majority of the credit or blame for this, depending on how this talk goes. And then most of what I'm going to be saying is using kind of automotive terminology, but it will apply generally to any kind of safety industry here. In case people are interested, there's some other talks that you can reference that kind of feed into this. A few years ago, there's a talk about kind of address space isolation, which was kind of the light bulb moment for this concept. Back in August at OSS Europe, there was a good talk about just the problem space in general and why things are very difficult to do safety with Linux as well. And then this morning there was a session on the safety MC where we got a little bit more detail, and this is kind of a continuation of that. If you don't remember anything else from this talk, here's what I want you to take away from this. Safety is very hard. It's a different kind of work than you might be normally doing as an engineer. I worked over a decade in the mobile space, putting out a ton of products and chips at a very high volume. Quality there was very important. Safety is a completely different beast. It takes a different kind of work to do that well. And that's different in terms of just the actual effort spent, the type of effort, the cost of it. It's just different. Safety varies a lot. So you can take a given safety solution, on your chip, put it in a slightly different product, and the requirements could be totally different. You could take that same chip and use it in a different market, completely different requirements. There's not a good one-size-fits-all solution for safety. You'll hear a lot about things like address space isolation. Usually people are talking about security for that. We want to protect the kernel from malicious intruders, from subverting the system. Our concept is kind of the reverse of that. So within the system as a whole, we want to protect our safety critical code from the kernel itself. Not because the kernel is bad, but the kernel itself has bugs in it. And that's a big problem for safety. So we kind of take a different approach than security. We want to protect the system as a whole. I don't know how many people were in some of the safety related talks here, both this morning in the safety MC, and there was a talk yesterday in one of the referee tracks talking about trustable expectations or testable expectations. This morning there's a lot of talk about formal verification and requirements and documentation and things like that. All those things are interesting, but it's only kind of part of the problem. When you're talking about safety, safety is more than just quality. Safety is more than just testing. You have to make some claims about the system, and you have to be able to show evidence behind those claims that you're making. So, at least from NVIDIA's perspective, a lot of the things that we've seen talked about here, I found the dynamics very fascinating. But to me, they are all very focused on quality. Everybody had a different approach to how they wanted to demonstrate quality within a given system. And in a lot of ways, there's a number of different ways you can demonstrate quality, and a lot of different valid ways. Our perspective, you use whichever method you find best for you. We've been doing safety in the traditional way, which I'll kind of show you how that works in a bit. But for us, the traditional way is sufficient. The challenge with it, at least with the Linux kernel, is doing it for completeness. So that, imagine you're doing formal verification on one function. That function works as expected. You can demonstrate that exact behavior. It's provable. That it's very high quality. So that function on its own, you've got very high confidence in its behavior. It's high quality. Put that into a system with a lot of other functions that aren't tested in the same way. Those other functions can have bugs in them. They can interfere with the execution of that function. They could overwrite data. They could overwrite stack. There's no isolation there. So when it comes to safety, if you're applying these kind of traditional methods, you have to go 100% out to the edge of your safety boundary. For the Linux kernel, it would be the entirety of the Linux kernel itself. If you're going to take kind of a function by function way of assessing quality and making sure nothing is misbehaving. That's kind of a very hard sell. That's a big uplift, and I'll show you why. So we're taking a little bit different approach to that. Really quickly, here's what safety systems look like. Or at least the kind of safety systems I'm kind of talking about at NVIDIA. So safety has been around for quite a long time, but with the kind of advent of AI, these systems are coming out into the physical domain. They're coming out in the form of autonomous vehicles, humanoid robotics, factory robotics. Basically, any machine that's going to be moving on its own, interacting with the physical environment, is going to need safety with it. And these things are going to have, or pretty much all of them are going to have AI in them at some point if they're not already there right now. So that's a big reason to have Linux for safety in your system. All these AI stacks, they run best on Linux. That's where people develop, that's where people deploy. So Linux is kind of the desired environment for that. Really quickly, just to give you an idea of just the kind of work that goes into safety. Safety needs to be part of your software development process, your hardware development process, and you need to have regulatory compliance as part of it. That needs to go in your all the software hardware you build. It needs to go into the systems you build. How you select peripherals, how you select sensors that go into the system. All these things become part of your safety story. And when you bring AI into it, you're doing a lot of machine learning ops. All these things have to be done in a safe way. That you can tackle that in a lot of different ways. You can prove the code is safe. You can make diversity arguments, but you need to have a way to do that, and then you need to have a way to certify it. There's a lot of components that go into making something safe. This one's kind of hard to read, but I want to point out the architecture diagram kind of in the middle of this. This is what NVIDIA deploys for autonomous vehicles. It's called DriveOS. We have, the traditional NVIDIA compute capabilities like CUDA, TensorRT. There's a whole bunch of libraries that go with that, media, pipeline configuration management, safety libraries. All of this runs on your choice of operating systems. You can run on Linux, you can run on QNX, but today, only QNX is safety certified. So when we take all these parts together, we can only make a claim about a product if the operating system itself is safety certified. It runs very well on Linux, but Linux is not safety certified, so we can't make those claims about Linux right now. And that's the kind of problem I want to address. If you're new to functional safety, this is the one thing to remember about it. It's the absence of unreasonable risk due to malfunctions in your system. So a couple big questions here. How do you define risk, and who decides if it's unreasonable, right? These are kind of very ambiguous terms, at least as written here. So risk comes down to a lot of different things. It could be a per manufacturer, per market argument. It's going to depend a lot on your device. So if you've got a robot in your factory moving around, something, if there's a safety hazard there's a complication, it's very simple for it to just stop. That's usually a common mitigation factor for robotics in factories or warehouses, something like that. If it's an autonomous vehicle, you're going down the highway at 100 kilometers an hour, you don't want to do the same thing. You've got a much different risk tolerance. Your car can't just stop in the middle of the highway. You're going to cause a pileup. That's an accident. So your bar for safety is a little bit different there. Your risk tolerance is a little bit lower. So there's a bunch of different standards that guide all of this. We won't get into those. Safety requirements for a system. When these things are out, in the physical environment, physics come into play. So this particular example, this is not my car. I think this is Igor's car. But if you can imagine a vehicle moving 100 kilometers per hour, it's going to take 36 milliseconds for it to travel 1 meter. So if you think about a person doing this, a person is constantly observing their environment, making decisions about, do I need to go left, right, slower, faster? Do I need to make any adjustments? These autonomous machines are going to have to make decisions about their environment in a very rapid time frame, very small number of milliseconds. And this includes those kind of full pipelines I showed you a picture of earlier. These machines are going to have to take in input from their environment, sensor input, all that kind of thing, command input. They're going to have to reason about them, and they're going to have to output some actions, and then those actions have to take place within a certain amount of time. And if you look at current state of the art like chat agents, you type in a question there, it'll go think for like 10 seconds or something. These machines have to do it much faster. But this kind of guides kind of where safety requirements come from in this environment. So why is safety challenging for Linux? Linux is not designed with safety in mind. For those of you who work with safety, traditionally if you get buy something from a vendor, you'll get a nice safety manual with it. It'll have an architecture and design that you can use to build up your system. Linux doesn't have a formal architecture and design, at least the way that's sufficient for most safety cases. Linux is a community-driven effort. If you have a safety requirement to have a certain coding standard, to have certain static analysis rules in place, we can't just go out and tell maintainers, all right, now everybody needs to clean up their code and follow my guidelines for this. That doesn't really work. That's not a Linux process. The bigger problem, though, on the technical side, Linux is a monolithic architecture. It's a common address space within the kernel. That means everything within the kernel has the same privilege. But there's no real kind of fault isolation between different subsystems in the kernel. So that goes back to the point I made earlier about completeness. One misbehaving thing in there can interfere with something else in the system. And if you've got a low risk tolerance, that can be pretty concerning. And of course, everybody knows that the Linux kernel is pretty large, pretty fast moving. Traditional safety. So for those of you who've never seen it, you basically start fully defining the requirements, architecture, design your system, then you start breaking it down to smaller components. By the time you're ready to code it up, you have everything fully specified, function definitions, good documentation, everything you need, write the code, and then you kind of work up from the bottom, work up to the top right again. You test everything against the specs that were used to design it. Function, unit tests, integration tests, system level tests, all that. At the end of the day, you've got a whole bunch of design documents. You've got a whole bunch of testing artifacts. You've got traceability between them. You can demonstrate. You've got evidence that you can support the claims you're making about the system. This does not work at all, really, for Linux, or at least the entirety of it. Something else that's kind of true about safety certification in general. This is not specific to Linux, but definitely applies to Linux. When you're doing safety certification of code, you want the code to be as simple as possible. You want to be able to accurately describe its behavior and test its behavior. So simple functions are better. Once you start getting more complex functions, stateful, broader ranges of inputs and outputs that are integrated together, those become very difficult to certify, both in terms of effort, but then even then, if you go through that the work of doing all that, I would really kind of challenge the accuracy of it. Did you really capture everything to the fullest extent necessary? And for the Linux kernel, at least, the most valuable parts tend to be some of the more complex parts: scheduler, memory management, all these kinds of things, networking. So that's a big challenge. Just doing that work is much more difficult than simpler functions. Just to put some context around that, so imagine you did a traditional safety certification. You spent 1 year doing that at an ASIL B or SIL 2 integrity level kind of thing. With all the work products you're doing, all the testing integration work products you're generating, you could end up with a number, roughly 1,500 lines of code written per engineer per year in that system. And then if you kind of scale that up to the Linux kernel as a whole, we're not using all the Linux kernel. Any given compilation of it will use a smaller subset. But even using 5% of the Linux kernel code, you're still 1.5 to 2 million lines of code that you'd have to safety certify. And using kind of these effort estimates, that's going to take over 1,000 engineers, 1,200 engineers, something like that to do. And the cost of those engineers is not insignificant. I mean, you can plug in your own numbers here or there, but in the end of the day, you're going to end up in the order of hundreds of millions of dollars to safety certify a Linux system to the fullest extent using a traditional method. That's really hard to do. So, a few ways people typically approach this. An out-of-context element basically means something that its behavior can be fully described without any input or influence from things outside of it. So basically something that's reusable or modular. So a lot of people will say, all right, I've read the standards, I know what to do, it's just work, we're going to jump in, we're going to safety certify the entire extent of it. Once you start doing that, you realize this is challenging, there's a lot of effort here, you need to start reducing scope. We need to start cutting features out. You've already cut it down to 5%, let's cut it down to 2% or something like that. A lot of important things get thrown out. Debugging capabilities, nice to have features, you trim it to bare bones. At the end of the day, you're still left with something that's very large, very difficult to do. Moving on from that, another approach we've seen people take, all right, there's a lot of effort with the kernel itself, but let's take that, let's package it with some external monitors, and then we'll call that the safety element. So that approach, avoids a lot of intrusion in the kernel itself, but by doing all your monitoring externally, you have other parts of the system that are then highly coupled to Linux. So these monitors could be a hypervisor, they could be an opti, they could be in a different component outside the CPU, but those things have to monitor the Linux kernel. And imagine you want to monitor, let's say, K-thread behavior. These things are spawned dynamically. So then you need to start informing these monitors where to look for things. And because of some of these physical constraints I mentioned, you might have to respond to something in 10 or 20 milliseconds. So then this external monitoring has to become very high frequency polling. That's a large amount of work you're doing just to monitor it from the outside. And then you can further zoom out. You can say, draw your box at a much bigger boundary, and then analyze that. That's kind of more of an end of production line approach, where it's no longer a modular reusable component. You can certainly do that, but most manufacturers that I've seen are not, building an entire system from scratch. They're taking chips and software from various other companies and vendors. They're integrating a system and they're building it all. So taking full responsibility of all the hardware and software in that system becomes very challenging. So the approaches to kind of qualification I've seen, they don't fully address the full scope of the Linux kernel. It's very effort intensive, and they missed a kind of key aspect of it, or at least nobody's really addressed it to the extent that NVIDIA felt would be useful for our systems. And so there's a problem that we're calling the Linux kernel spatial interference problem. So that's safety terminology, but in interference is basically something that might prevent you from achieving your safety goal. Spatial interference is something not happening where it should. So that's a bug. That's an array using an incorrect index. That's a buffer overflow. That's a stray pointer. These are all kind of spatial interferences. And because the Linux kernel is monolithic, and because it's very difficult, time-consuming to prove out every single line of code is operating perfectly, the kernel itself is subject to interference from safety goals from a variety of number of sources. I mean, we have LTS kernels that are chock full of bugs that are found after the fact. Bugs are just there as part of large systems. So when you've got a very low risk tolerance, you've got a lot of bugs. You've got a lot of bugs that are discovered after production release. That becomes challenging. So what does this look like in reality? So if you've got green box top right, you've got a safety critical process. You can imagine that has safety requirements down on various device drivers. But the Linux kernel is monolithic. So there could be other sources of interference within the kernel, buggy drivers, buggy code. They can cause problems with other parts of the Linux kernel itself. They can cause problems with user space. If you've got a low risk tolerance, then this can be a challenge. So NVIDIA's approach to this is to kind of narrow down the scope of where safety applies and to put some boundaries around it. So rather than saying we need to go out and safety certify 100% of the kernel, we're going to put some mechanisms in place where we only need to safety certify the part of the code that has safety requirements on it. And we're doing so by creating something we're calling a context here, which is just another way of saying a different set of page tables. So if you create different page tables, you can create, a different set for each integrity level, your lowest level of safety all the way up to your highest level of safety. And then we introduce some directionality in write access in the system. So if you like, and again, these are the automotive terms, but if you look at QM, which is quality managed, your kind of lowest safety integrity level in the system, basically your non-safe code, all the way up to ASIL D, which is your highest integrity level, most safe and trusted code. We've set up our contexts such that there is the entire system can read everywhere, but you cannot write to somebody with a higher privilege level than you. So your QM code, which is the vast majority of your kernel, now cannot write to any of your safety-related code, which is typically at an ASIL B or an ASIL D level. Your ASIL B code can write to things that are classified as QM, and that's okay because you've done some diligence on it and you have a good understanding of the behavior there. You've got high confidence in it, and then the ASIL D, which is your most trusted code, it can write to pretty much anywhere in the system. So how's the picture change? So you've got that same safety application. It has an integrity level assigned to it. You still have the same safety requirements on those device drivers, but now because the contexts are aligned, basically common memory map between parts of the kernel and user space that's using it now. Now there's a hard barrier within the kernel where those same bugs can no longer interfere with either the kernel itself or with user space, actually, in this case. And so by doing that, we don't have to extend safety to the vast majority of the kernel. That stays kind of in the yellow box. We don't have to care about that. And we don't have to worry about undiscovered bugs there. Because if they're a spatial interference bug, if it's a straight pointer, that kind of thing, we have an MMU enforced mechanism to protect our safety critical code. So the interesting things about this, nothing really needs to change for the code that is not safety related. Nothing needs to change in terms of process. The maintainers don't need to know about things outside of a few critical areas. We don't need to do anything else special like that. There's no really change in process. It should be kind of transparent for the vast majority of the community that's not doing this one specific thing inside the kernel for safety. There's also temporal interference. So temporal interference is basically something not happening when it should. So again, the scheduler could be a course of that, a message being delayed or not delivered at the right time, a stuck interrupt. So we have to do some additional things to protect against that, but that's not our biggest focus. It's part of our solution, but the state of the art there, at least in terms of watchdogs, heartbeat monitors, those are okay to solve these kind of problems. Okay. All right, so how do you apply this? So first thing we have to do is basically dimension our memory for safety. So all your memory pools, get a safety dimension added to them. And we have to go and find all the places in the code that we actually care about for safety. So for our systems, that's all derived top down from safety requirements. Your vehicle is going to have requirements in the operating system, so those will get translated down. There'll be requirements on something like a device driver. So we identify safety requirements like that, and we add some kind of context switching around those very specific functions. Context switching in this case means just swapping out to a different set of page tables. There's some trade-offs with this. We're increasing memory utilization because now we're segregating some memory for safety reasons. And then anytime you're swapping out page tables, you're doing more work on the CPU. So there are some kind of trade-offs when we bring safety into the system. This is kind of what it looks like before. If you guys have seen this slide, I stole from Igor. But basically, with this technique, all right, so you dimension the memory. And then when you're making a memory allocation call, at least in our case, we're passing some context to the memory allocator environmentally. That's the context selector up there. The memory allocator itself, it's one of those complex subsystems. We don't have to worry about safety certifying that. We can apply this technique pretty much to all the memory allocators in the Linux kernel, probably user space as well. The memory gets allocated, comes back, and then we do an end-to-end check. Do we really get a buffer out of the right pool itself? And then we do safety around the context selection and the validation that we got something right. But with this method, we can kind of, it kind of applies a little bit transparently to some of these cases. Context switching. This is a very simplified example. But so imagine you've got that safety critical device driver. Device drivers depend on a lot of library functions, a lot of framework functions to do their work. A typical thing, all right, I want to print something. You enter your driver or print hello world, whatever it is. I don't want to go through the work of safety certifying printk itself. The vast majority of its uses are not safety related whatsoever. But if my safety critical driver calls that, before getting into the code, I'm going to switch out my page tables. I'm going to run printk itself, and then I'm going to switch back. So I'm not going to really care if printk misbehaves. It does a stack overflow or corrupts a buffer, because my safety critical code is protected from that. It gets a little trickier when there's nested dependencies. So if you look at something like zalloc, we're going to do the memory allocation as I described, but then you need to write to that buffer before returning. You need to zero it out. So we need to go find all these cases that are nested dependencies, and we need to also bring those into a safety context. We need to do some analysis on those. And in this particular case, after we do the memory allocation, we're going to change our page tables again. We're going to go up an integrity level. We're going to allow memset to write zeros to that page. And then when we're done, we're going to walk backwards to our function, context switching back. So the trick in this method is finding these kind of nested dependencies. You want to do this ahead of time. You don't want to play whack-a-mole as the software is deployed and up and running, and something critical pops up. So the key part of it is doing kind of call chain analysis and finding all these areas that might do some writing to your safety critical memory, and doing some analysis around those.
What kind of overhead do you see? Like if you're in a driver and you're doing going between the different contexts quite a bit, it sounds like, and going and swapping out the page tables.
Is that mic working?
What kind of?
Okay, all right. Just making sure it's working. Okay. I heard. I just didn't make sure it worked. It depends. So and that's the key here. So if you define your system where it has safety requirements everywhere, you're going to be doing a lot of this. So there's still a need to minimize your safety requirements on Linux, and still do it in an intelligent way. So it takes some very intentional application to do this. Let me show you this next example, and I'll continue answering that. So for us, as we're building this out, what it kind of looks like is, we will start initializing the system. During kernel initialization, all right, we need to dimension the memory. So we're going to be doing that. Other parts of the system start initializing that have safety dependencies. So we start doing context switching a little bit during system initialization. For us personally, for a lot of our needs, our safety requirements map to device drivers. They don't necessarily map to broader parts of the system. And even then, within device drivers, they tend to map to the initialization phase. There's not a ton of things that really map to runtime safety requirements from our systems. Your mileage may vary on this stuff. So for us, we find that there's a lot that the overhead is incurred during initialization time. That's a challenge. It's something we're going to be minimizing. We're going through the process now, so I can't tell you a percentage or something else like that, because we haven't fully fleshed it out yet. But it's noticeable. It's there.
It's not very different from what normally happens with user space. You have other space ID identifiers so that you can optimize the TLB utilization. So it's the same.
Which are these ARM environments? Are these x86? What are these?
So for us, we're developing on ARM systems, ARM 64 based systems.
Was there a question remotely?
Yeah, I was going to ask for the context switch. Are they kind of, if I understood it correctly, it's all done automatically and doesn't have to be like manually instrumented, right? Brian?
There, so that is another key part of it. When you identify these functions, you need to have some way to instrument that basically. So we're developing techniques to do that as well.
So it's not like something like a thread is marked as it's an ASL AB or whatever or QM, and it automatically
it's not
switches
on a
back
per
and forth.
thread basis.
Okay.
Yeah, it's not on a per thread basis. You're really looking at on a per function kind of basis.
Okay. By the way, good to see you here. I haven't talked to you in a while.
Yeah, find me afterwards. So yes, I mean, if you're looking at safety on a per thread basis, then your scope of code that's included could be rather large and very dynamic. And from what we've found, that's not really necessary. We don't need to, at least within the kernel, have a ton of this context, a ton of the execution in safety context. So we're able to really minimize the footprint where these safety requirements are applied and just do, number one, safety analysis around those, and then isolate those functions from the rest of the system that we're not doing analysis on.
So
Yeah, I can imagine doing this for small things, but I mean, this gets awfully complicated pretty fast, doesn't it? I can just imagine things like you couldn't do this with NMI-based profiling, right? Because then all of a sudden you have to worry about the NMI handler interrupting your stuff, and the NMI handler probably isn't certified like everything else is or validated.
Correct interrupt behavior is part of the system that needs to be provably safe. So what aspects of the interrupt subsystems I can't speak to. We can talk to Igor afterwards about that, but interrupts, at least part of interrupts, are in scope for safety.
So when this is done, how invasive does it get? Does the kernel need to be changed quite a bit in all these locations? For example, does KMemset need to get changed? KZLX needs to get changed? Or is it going to be like not as invasive?
Yeah, I would say I think
I'm
this
going-
is probably, this would have been a really nice topic for the memory management track here. This is, there's seems to be a lot of impact to memory management here. If everyone do this upstream, I think that's a good group of folks to talk about this with.
Yeah, definitely. Yeah. So to your question, Saravana, the impact is less than you would think. So when there are safety critical functions, we have to have a way to identify those. The rest of the behavior, a lot of these things can be behind the scenes. So the memory allocation behavior I described earlier, all the callers of that do not really need to know anything about safety or non-safety. Context is kind of identified in your address space. The selector is kind of aware of that, and then that's kind of implemented a little bit better. There's a couple changes to the memory manager to do that, but the core algorithms themselves are not changed. So the changing kernel functionality is less than you'd think.
And then one last question. I was kind of leading to all of this, to this question. You talked about all the different options, the solutions you've tried and considered. What is the thought? What's your thought? I'm sure you thought about this. Running these different components in different VMs and still letting them work through, say, VirtIO or whatever mechanism of communicating between VMs. So that still gives you read access or protection depending on how you configure it.
Yeah, so there's a lot of different. There's a lot of different ways to build out safety systems, but if you want to have all your safety code in VMs talking to VMs and not running on Linux itself, that's perfectly fine. You could have
they could all be Linux at my point, right? You could run multiple instances of Linux inside multiple guests. Yeah.
When your VM is running on Linux, then you still have the same spatial interference problem. The kernel can still interfere with the VM behavior. It can still interfere with user space behavior. Nobody's going to chop up their application code into tiny little slices and do a dozen different or 100 different VMs for that. It's just not performant. Typically in systems we deploy in Drive OS, there's a single VM.
Yeah, I think people approach these problems in two different ways. You can take it, slice up in a bunch of pieces and try and glue them back together. Or you can take what you're doing here, which is take the big, unified piece and you're trying to chop it up into littler pieces. So I think there are two different approaches to the problem and neither one of them is more valid than the other. So
yeah,
this happens every time that people try to do this.
Yeah. So as I said, we're trying to protect things from the Linux kernel itself, protect other parts of the kernel, protect user space from it. And so that's what this approach is about. Okay. This diagram is written from a safety perspective, but it basically says a majority of your code in the Linux kernel, and this is not drawn to scale, but a majority of your code in the Linux kernel stays at QMs. It's not safety related. We've got a monitored boundary, which is basically just a hard safety mechanism to separate your non-safety code in Linux from your safety-related code in Linux. And then everything that's safety-related, we do safety qualification on in whatever way makes sense, a V model, formal verification, whatever. But that's all on one side of the boundary. All your non-safe code is on the other side of the boundary. And then with these mechanisms, our particular one is hypervisor backed, but we use this to build up all the rest of the capabilities you need in a full safety system, file system access, IPC, safe syscalls, everything. It's not just us. You know, we like this idea. We came up with this idea. We took it to our automotive assessor. We explained it to them. They looked at it and said, well, when implemented, you know, as described, we expect this to meet ASIL-B of the current ISO 262 version 2 standards. And this was a kind of key moment for us. It really kind of gave us a lot of confidence in this approach that, number one, we could do in a way that does not impose a lot of burden on the Linux kernel community and can be done against existing standards. We don't need to wait for standards to evolve to kind of meet us. Evolving standards will be a little bit nicer, but we'll be compliant with those as well. And to kind of further this concept, as of last week, we've joined ELISA. So we intend to kind of participate there and start discussing some of these mechanisms with the community as well. In particular, I see a need to talk about kind of context definition and management and the memory allocation semantics around all of these things. My hope is that this will prove to be valuable. This will have some longevity into it, and there'll be some value to this for the upstream community at some point. So that's it. We can get into more questions if people have them.
So if you have something like the rear view camera, and that'll go over the network, and there's the federal mandate with the 2-second, like with the ASIL Bravo, that is your scope of certification still pretty large? Like, would you have to bring in the whole network stack, for example, like mark that as critical?
It's hard to speculate on that. It comes down to how the system is designed. So a 2-second camera preview for safety. I mean, there's a million ways you can design a system for that. A lot of people offload. With this example, if your system boots up fast enough, gets to Linux fast enough, we can initialize fast enough, then you could use your Linux kernel camera drivers to do that potentially. And so that's kind of one difference in this approach. And we can do that without having to safety certify, let's say, the entire V4L subsystem. So highly contextual, depends on your particular design, but could be done. Way in the back.
Is there any change that you're making to the kernel as part of that effort that you plan to upstream?
Yes. So we need to add some code in the kernel to, like I said, create context to manage switching between them, to manage, you know, which functions are in safety context. And there's going to be some key parts of the kernel where, I mean, we just need to verify that behavior actually is correct. There's some key, you know, memory allocation, page allocation functions that, you know, we will need to, those will be in scope. So there'll be some part of it, but the vast majority of this stuff will not require attention from maintainers.
Was the question there whether it is upstream or? Oh, okay.
Yeah, like I said, I mean, we're developing this concept right now. We hope it has a lot of value for any kind of physical AI system, robots, cars, whatever. And if that proves out to be true, then I can imagine, typical thing, you want to do multiple product generations. We need to get this stuff upstream for that reason. We're kind of coming out a little bit early because we hope it'll go that direction. So we want to start engaging on some of these things as soon as we can. Okay.
Oh, is there one online? Go ahead.
Can always count on Saravana.
I see one raised hand if somebody wants to ask a question.
Oh, sorry, it wasn't. I forgot to lower my hand. Thank you.
Okay, that's it. Thank you.
All right. Thank you, everybody.
Let's see. And I guess we could even just start putting your slides up now. So yours should be, is that one yours? Okay. Okay. So we'll just have that up and then you can go through the slides like normal. Okay. Okay, so I can put. Yep, and you can put that wherever you want. Okay, thank you. Sure.
You said RT, that was my first thought. Okay, Steve, it's going to be. But it's good they're doing early than expected.
Most of the things that come out now, from the beginning, I think that you got to accept that way. So using game, for example, was just right now, you say, well, it's not all on the arm of the practice regulation. Some special other features.
Sanjay, right?
Yeah.
And Dave again. Good to see you.
Nice to meet you. Actually, I have made a problem that is I uploaded wrong slides, and this is the correct one. So I'm trying to fix this.
Thank you for uploading them, by the way.
Sorry?
Yeah, we can fix it. Yeah,
okay.
let me know if you need any help. So probably can't do it any faster than you can, though.
Okay. Okay. Sorry for the problem.
Oh, yeah, no problem.
I think this must be.
That's good. Yeah, and so I'm just in the room to shepherd if you need any help with anything. I'm supposed to give you the time warnings. Do you want to leave any particular time at the end for questions, or do you want to?
Yeah, I wanted to be able to time for training.
Okay.
I'm trying to make the kind of
So I'll warn you at 5:35. It's 5 minutes. So I'll give you the 5-minute warning, but you got a 10-minute.
So just 5 minutes warning, but
Oh,
usually be 10 minutes.
Yeah, so I'll do this. Just to
Okay. I think I will try to distribute your
Okay, sounds great. Yeah, let's give you this at the very end. So, you want an introduction, happy to do it, or you can just.
Okay, it's the time, so let's begin. So thank you for coming to this talk after the great coffee break. Hope you had some coffee so that you don't sleep during the talk. Yeah, so my name is SJ, and I'm maintaining a kernel subsystem called Daemon, and currently working for Crusoe, and we are hiring. And also, I should note that I was working at Meta when I submitted this talk. That's why the presentation is saying that this is for Meta, but it is also all open sourced and upstream. So, and all opinions are my own. So hopefully this will be not only for Meta, but also you. Okay, so I will do this talk in this way. I will firstly give some background and introduce how we implemented the page level monitoring in Meta and fleet-wide monitoring at Meta, and then have some Q&A. In short, just set your daemon stat enabled default kernel option, and then you will be just happy at observing the data access pattern. And why Meta and you would need the data access pattern observability? That's because the data is what we love. Data is the precious things that making our money, that's the source of the money. However, the data should be placed on something, some physical thing, that is the memory devices, and we all hate memory, mainly because it's money consumer, not the generator. And also there are diverse types of data and memory devices, and therefore managing those efficiently is some kind of interesting and challenging, and that can save money. And what is the efficient memory management? Because data is precious and memory is some kind of money consumers. We could say that if we can keep more precious data with less memory, then that could be some kind of efficient management, I'd argue. And that means that we need the data access pattern to make such kind of actions on precious data or non-precious data on expensive memory and less expensive memory in some different ways, so that we can keep more precious data with less memory. And also we need to self-aware ourselves and assess ourselves about how we are doing, how efficient we are doing, if there's some room to improve, and repeat continuously. That's how we get our job secured, right? So what is Daemon? I will try to do my best to introduce it in very simple way. So what it does is it is spawning a kernel thread that works for Daemon, and it shows if each of the page of the memory that you want to monitor the data access pattern of at every 5 milliseconds, and then inform users the findings of the accesses every 100 milliseconds. And the time intervals can be tuned by yourself manually, or just ask Daemon to do automatically. I will present a little bit more about the auto-tuning in this talk. So as a result, Daemon can provide you the data access information, including location of the access, frequency of the access, and how stable the access frequency is, and the frequency and stability means that you can also know the recency. It is, I told you that it is seeing the access to each of the page, but it is not in real because it is too expensive. It utilizes a kind of sampling and aggregation mechanism that adaptively can be applied for best effort accuracy with minimum overhead. As a result, the upper limit overhead can be tunable by users as much as you want, regardless of the memory size. That is, on 100 gigabyte system and 1 terabyte memory system, the upper limit overhead should be same as you want. And with real workloads, we have shown that it is consuming less than 0.01% single CPU time. We don't know the exact number because I was using the PS command to see the CPU consumption, and it was just saying 0.01%. 0.0%. I don't know what was the real number under the digit. Nevertheless, even though it is designed to be lightweight and scalable, you can also utilize that for page granularity or fixed granularity monitoring. And also, if you want, you can also give it more and more resources as you want. You can even use multiple CPUs to scaling up. It is now available on off-stream kernels. It has been merged in 5.15 and not yet rebooted. And it is enabled on almost every major distro kernels, including except Ubuntu. It is faster. And also currently being used by some real-world products, including AWS Aurora Serverless and SK Hynix HM SDK, and some of the researchers. And Daemon is for data access monitoring, but it also has a very important second named feature called Daemons. It stands for Daemon-based operation schemes, and it allows users to just ask Daemon to do some kind of access-aware system operations by just specifying their needs. This feature turns the Daemon into access-aware memory management system operations engine, and it is out of the scope of this talk because this talk is about the monitoring. However, it turned out that Daemons is also can be useful for monitoring, so I will take that in later slide. In one sentence, Daemon can be told it is a Linux kernel subsystem for efficient access monitoring and access-aware system operations. And also, we have a community waiting for your selfish discussion. We are doing that kind of selfish discussion very actively in personal and in public place. So if you have any questions or needs for help, please feel free to reach out to us in public or private, whatever you prefer. So first, let's talk about the page level monitoring. So about 1 year ago, I joined Meta just before the LPC, and my first project was giving some data access pattern observability for Meta's fleet. And the first motivation for this work was that at that time, we were able to see the data access pattern like showing this. And also Meta was investing pretty much for making huge pages system better for their fleet. And then I introduced Daemon to my colleague who was working on huge pages, and he asked me, okay, so we found the 2 megabyte region starting from address of 4 gigabyte, and it is accessing at least 1.3 times per second, and this access frequency has been kept for last 3 hours. It means that it is somewhat useful and something that can be valuable. And is this a huge page? That was the question from my colleague. Actually, the information is a kind of, I was unable to say yes because Daemon doesn't have the information, mainly because Daemon is working on an abstract called regions rather than the pages. However, I realized that Daemon is knowing that more technically speaking, not Daemon, but Daemon is knowing that because Daemon is making the system operations in page level, and also it is providing a kind of feature called filters that can filter in and filter out the target memory to make the memory management action based on their type, page types. And therefore, we implemented this page level monitoring support. For this, we have modified Daemons and Daemon interface to let Daemons provide the information about how much of the memory the filter has been passed, how much memory has passed the filter to Daemon, and then modified Daemon's user space ABI to expose it to users. And also, we needed to update user space tool for better visualization and collecting of the new data. As a result, we were able to answer to the question. So this is the data access pattern visualization using Daemon user space tool. And from here, we can say that this 816 kilobyte region starting from address 4 gigabyte was accessed at least 1.3 times per second, and the frequency has kept for 3 hours, and this is backed by 2 megabyte huge page. Maybe we are doing good. But also we found that there are 3 gigabytes of memory regions that not accessed at all for 3 minutes, but 20 megabytes of the 3 gigabyte memory region was backed by huge page. Maybe that can be revisited later for better optimization, but this is what we can now see with that. And also, Meta has contributed many code for this feature. Usama Arif, who is my ex-colleague, has contributed the huge page size filter, and Nyat Pham, who is the maintainer of CSWAP, has also contributed yet another filter for finding active pages, and also Yue Yang, who was an intern, also added some support. As a result, we were able to use this page-level access monitoring in real-world workloads, and the results were something like this. So we were able to break down the data access pattern of the systems of the real-world workloads based on page types, like what is the access pattern, or specifically the idle time, the time that the memory was not accessed at all, was for anonymous pages, file-backed pages, unmapped pages, and huge pages, and etc. The full list of the supported filter types are like this. We can do filtering or do the monitoring in page level for file-backed pages, anonymous pages, based on belonging C groups, whether it is young or not, marked as young or not by the reclaim logic, and the size of the folio, which is I have shown you with the huge page filter, and whether that is on active RLU list or inactive RLU list. Maybe in future we can extend that for MGRLU, like based on generation of the RLU, but such kind of future extension can also be made on demand. And there are some remaining works that is, this is page level monitoring, and therefore we need to do something based on page level. That means that it is expensive and unscalable when the size of the memory goes larger and larger, and therefore it is not really applicable in fleet level as is. One workaround is kind of having machine level sampling. That is, if you have 1 million machines of a fleet, then maybe you can run this monitoring for only about, say, 1,000 number of machines. That could be still high overhead, but wouldn't really impact your high level performance of your service. And also, in this term, I'm saying that this is doable because for page level monitoring, you need to do the breakdown or the filtering in page level just once. Then you can get the snapshot and you can disable the page filtering. And that said, I want to do further optimize this, and the idea is to do some kind of page sampling on top of this implementation. However, the timeline is not yet clear at the moment, but if you have interest, please let me know so that I can prioritize or send patches directly. That was about the page level monitoring. Any questions so far? If not, I think we can further move to the next topic. Then second topic of this talk, the fleet-wide monitoring. This will be a little bit longer than the page level monitoring. I will introduce 2 major changes and the final interface for doing this. First of all, we had to implement the monitoring intervals auto-tuning. What is the monitoring intervals auto-tuning? But before answering that, what was the motivation? The motivation was that there were people who were complaining about daemon's accuracy. That is, people were trying to use daemon on their workloads, following the getting started guide on the project website. However, what they found was that it looks like just random noise or just something that makes no sense. And that was because daemon parameters need to be tuned for given workloads and system. Without tuning that well, the result would look only chaotic or very boring. I will explain this a little bit more, but anyway, so all daemon successful users have gone through that kind of time-consuming tuning experiment. And at Meta, I wanted to run daemon for all the fleet-wide workloads, and Meta is running more than one workload, right? They are not running only Facebook, but also Instagram and etc. So I didn't want to do that again. I have done that when I was in AWS. I didn't want to do that anymore. So we started developing the auto-tuning of the parameters. But before saying that, why the tuning is required, that is, what we want as an output of the daemons monitoring research is that having some actionable amount of diversity in terms of the access, right? We want to know some kind of hot memory, but also we want to know how much of the memory are called. The snapshot should show such kind of variable pictures, dynamic pictures, colorful pictures. And if the intervals are too short, in this context, the intervals means the 5 millisecond and 100 millisecond I explained at the beginning of this talk. That is, if intervals are too short, then the output would look like very frozen, but without superstars like Elsa. So it is only boring and cold, worst of worst, right? And if intervals are too long, each of the snapshots will capture, at least say that every sample would say, yes, it was accessed. Within last 1 minute, yes, it was accessed. Yes, it was accessed. If the system is actively running the active workload, that would just look like the Muspelheim, the World of Flames, but boring because there is no door. And you can also think about just making sampling intervals very short. But in this case, yes, it will take more detailed information. However, most of the sampling would say that it was not accessed at all, and therefore it would not really show us good picture about the stability. And also, anyway, unnecessary CPU cycles are just waste of the resource and money. In real world, we were able to actually see that kind of frozen world having no Elsa and therefore just boring. And the histogram was also showing same thing. And by manually doing tuning, yes, I did the manual tuning again in Meta. I had to do that to show the idea. But anyway, by doing the tuning, I found that with 500 millisecond sampling and 8-second aggregation, it shows some kind of feeling actionable pictures like this. And the histogram was also look like something that we can expect. Therefore, we designed the intervals auto-tuning. So the idea was changing the question. We were asking users how we need to do monitoring. Let us know the sampling intervals and aggregation intervals that is instructing the daemon. But we changed the question to what the user wants to achieve. How much colorful picture do you want to see? And in this way, the users can specify the desired amount of the access event in each of the snapshots, the colorfulness, and the minimum boundary and maximum limit of the sampling interval so that the auto-tuning doesn't go too far. And the mechanism is very simple. Just tune the intervals for the desired goal of the colorfulness using a proportional feedback loop. If the current colorfulness of the snapshot is less than goal, then increase the intervals and vice versa. However, this also means that we are not removing the parameters, but adding yet another parameters. So this might sound like ironic, but I'd argue that this is kind of inevitable, and we just can argue that it is easier to tune because we were asking how to do that. Now we asking what you want. People may know what they want more than how they should instruct this kind of complex subsystem. And we also have a default suggestion that we believe it is good enough. It was proven to work on real-world production workloads that I will show more research. And I argued that this is the suggested default values are good enough to at least starting. And how the auto-tuning works in real world. So we have ran this auto-tuning feature on real-world workloads, and we were able to see that the auto-tuned sampling interval, which is shown in left graph, is showing dynamically changing based on the workload status, but eventually converge to some stable number. And also the right side is showing that the internal score of the feedback loop, it is also showing that it is converging to the desired number, namely 10,000 value. And how the auto-tuned snapshot looks like. So this is the snapshot of the data access pattern on the real workloads. So people may think different things. People may interpret differently about same pictures, but I was feeling that this is some kind of meaningful access patterns on the workloads. And also this pattern was very similar on different multiple workloads without manual tuning. And also it resulted in the less than 0.1% single CPU time consumption because we are not manually setting the time intervals. So that was the intervals auto-tuning. Any questions so far? Okay, I can move forward. And the second question was, what should be the format for the data access pattern of the fleet? There are so many machines in fleet, and for getting all the data from machines and then showing all of those makes no sense for human eyes. The numbers have to be aggregated. However, Daemon is providing location, frequency, stability, and recency, which are not easy to aggregate, especially the location information is only disturbing that kind of aggregation. That is, the output is showing that, okay, there is a region starting from 4 GB address and hot, but does that really matter on does the address does that matter in case of there are multiple machines? So we found that the location is only disturbing our work, and therefore we developed a format called idle time percentiles. Here, the idle time means that how long the given memory was not accessed. And the percentile is that of the statistics, that is, we sort the values and then get the first 1% position value as P1 or first percentile, and at the middle, the data at the middle is called P50 or 50th percentile. And by doing this way, we were able to make some more aggregatable format. That is, the left side is the unsorted snapshot or address sorted snapshot. And the right side picture is showing the same information, but dropping the location information, the address information, and then sorting the everything based on the access frequency. Then we can divide the lines to show divide the line to show the distributions of the values in sorted way, and then we can find P50, P75, and P99 by seeing the crossing point. And how it looks like in real world. So we have collected the idle time percentiles of, if I remember correctly, a few thousands of machines on real world workloads from our fleet, from Meta's fleet. and then plotted the data in this way. We were able to see that some kind of expected access pattern, and it was also as expected, they were having some common patterns and different patterns depending on what kind of workload they are. And the second data access pattern format is called cold memory tail. Actually, this is very same to the idle time percentiles, but it is just just changing the x-axis and y-axis. That is, x-axis becomes idle time, and y-axis becomes the size of the memory of the idle time. Arguably, some of the people argued me that this is more intuitive to understand better than the idle time percentiles. So I have implemented this and also tried visualization of the same data that I have shown with the previous slide with this cold memory tail format. So again, it was very like we expected, and also we were still able to see the commonalities and different features between different workloads. Any questions so far? Okay, I can move forward. We started from 50, so okay. We still have about 10 minutes, right? So this is the last topic of this talk. So what is daemon stat? So we implemented the auto-tuning for fleet-wide monitoring and also developed a format for aggregating the data, and we found that the aggregated data is showing some expected patterns. The next question was how we will deliver this feature to our fleet. That is, daemon is in kernel, so to collect this data and show that in some kind of rich pool and fancy way on our web browser, then we need to further implement a user space agent that will run daemon with the features, including auto-tuning, and then collect the monitoring output and send the output to a server, some kind of node collector that can be integrated with the Prometheus-like things. And I wanted to make this as simple as possible, and therefore we implemented a kernel module called daemon stat. It is running the auto-tuned daemon with very, very minimum number of parameters that were tuned for default use case, and then it exports the idle time percentiles and additionally estimated memory bandwidth with parameter files. This can be enabled at runtime or boot time using kernel parameters, kernel command line, and even can be enabled by default at build time using kernel configs and upstreamed on 6.17. It is utilizing the module parameters as the interface, so you can enable that by default in build time using the daemon stat enabled default, and also you can read the parameter files on the sysfs to get the estimated memory bandwidth, which represents the hardness of the overall system, and the memory idle percentiles in milliseconds as an array of the numbers of the idle time that divided by the commas. So now you can do the fleet-wide monitoring by setting the daemon stat enable default and then modifying your monitoring agent to just read the idle time percentiles file and then sending the content to the server. I actually did this by modifying our monitoring purpose agent, and it was pretty straightforward. So hopefully this is something that's doable in not only Meta, but any companies, including my new company. I will try to do that. So wrap up. In Meta, I developed and upstreamed the daemon features for page level monitoring and fleet-wide access monitoring, and it is all upstreamed and available in upstream kernel. So please feel free to use, and please feedback daemon with your selfish purpose. Questions? Yes, please.
From the insights you got from the fleet-wide monitoring, what were you able to change, or like what were the insights you got? And then, like, let's say certain workloads you found that there were hot pages, but there weren't huge pages. So could you, what did you do then?
So one of the example of such insight was whether they are suitable to turn on swap systems. That is, there was some systems that believing that they are having very uniform data access pattern, and therefore it makes no sense to, and also latency sensitive, and therefore makes no sense to enable swap at all, and therefore they were always switching to enabling swap systems. Meanwhile, Meta was getting a very big efficiency gains using swap systems, and also further investing on kernel subsystems for making it even more efficient, called ZSwap, which is really great subsystem and maintained by two of maintainers are working in Meta. However, and by looking at this, we were able to see that there are some commonalities in terms of the access pattern, say workload 1 and workload 2. Both are showing a kind of long cold memory tail or high idle time memory portion. So, and also that pattern was similar to another workload that were convinced at using swap system. So I was thinking that we could utilize this insight to convince the other workload who were using swap system to turn on that. Yes.
Pretty far.
And one thing that I need to further add is that, so I was thinking that, but I haven't proved that because I left Meta just after doing this.
So thank you very much. And I think the auto tuning is very interesting. So my question is like, is the auto interval tuning based on the assumption that the workload is kind of have a uniform memory usage or some like a repeatable pattern? If it is, then what if the usage is like very unpredictable or like real random?
I'm sorry, can you please come again, the very last part?
I mean, so if the auto tuning is based on the assumption that we have a repeatable pattern, then what will that behave if the like a usage is really chaotic or random?
Actually, the expected or our assumption under the auto tuning is that the system will dynamically change its access pattern. Technically speaking, the access intensiveness. Therefore, we need to auto tune because it is dynamic. And the real question was, I'm sorry, I forgot the real question. Can you please?
No, I just want to know like what kind of like assumption algorithm is based on.
Yeah, so that was the assumption. The memory access intensiveness would change over time, but also will eventually stabilize at some point. And then once it is stabilized, it will keep the stability for at least some amount of time. We also don't know how long the stability will go on. However, because it is auto-tuned, I was thinking that it doesn't really matter.
I see. So we assume that, or like we believe that they will like converge. Okay, thank you very much.
And also that was the case that we were able to see in real workload like this. That is, the access pattern was changing over time, and the tuned sampling intervals were also changing following that pattern. Any other question? If not, I think we have 1 minute yet. So if nobody raise your hand, then I think I can give it back 1 minute. Thank you.
Thank you. And it can be as simple as upscaling a 1080p stream to 4K or downscaling for multiple window playback or picture-in-picture scenario. And the next is CSC, the color space or color format conversion. This includes conversion between RGB and YV formats, which is essential because display typically operate in RGB, and most video codec surface come in YV format, such as MV12 and P010. So color space conversion sits at the very heart of any codec to display pipeline. And the next is rotation and orientation adjustment, another important category. The software or hardware need to support the rotation at 0, 90, 180, or 270 degrees, as well as the mirroring and flipping. These are used in camera pipeline, UI composition, and application running on rotated display or mobile phone factors. And the next is blending. It is also a core function. This includes overlaying multiple surfaces, for example, combining UI layer with video, or applying transparency or composite multiple planes in one output. And finally, HDR, video tone mapping. As HDR content became more common, tone mapping is required to convert wide gamut or high dynamic range videos into actual luminance capability of a target display. This is one of the most computational demand to the processing operations, and a major motivation for hardware acceleration in modern pipeline. Now that we have covered the core function of video processing, let's look at how these operations actually appear in real-world applications. Each use case forms a pipeline that chance decoding, color conversion, scaling, tone mapping, and or composition together. I will walk through several representative scenarios. The first one is SDR or HDR video playback. In a typical media playback pipeline, the following the flow start with file reading, followed by video decoder. Once the frame are decoded into YV surface, we may apply color conversion, scaling, and tone mapping before rendering. And these operations are required in almost every playback scenario, and efficiently accelerating them directly after battery life and affect battery life and playback smoothness. The second important scenario is the video conferencing. Video conferencing actually includes multiple parallel pipeline. For local webcam or remote paths, we start by capturing YV frames and then apply color conversion and scaling, and then encode the video before sending it over the network. And the second sub-scenario is for the receiving side, we receive it on a remote video stream, decode it, and then prepare it for display. And then it is the final scenario for local rendering. We took both of our local web camera preview and the remote video stream, applies color conversion and scaling, and then blend them inside the composite. And this is where the efficient 2D processing became essential, especially when multiple surveys need to be composed in real time. The third scenario is GAN DVR or GAN recoding. The pipeline starts with frame buffer recording, frame buffer rendering by GAN, which may be SDR or HDR. Before encoding or recording the stream, we typically perform color conversion, and then because the frame buffer is RGB, we need to convert into YLV, and then do the decoding, encoding, and sometimes scaling depending on the desired output resolution. The video is encoded and stored into the disk at the end. And the fourth scenario is cloud gaming, which is very similar to game recording, except the final stage is send a stream through a network. And the final one is transcoding. This pipeline reads a source file, decoding it, and then apply color conversion and or scaling, depending on the output requirement, and then re-encode the content before saving. Like the uploading process of YouTube. When you upload a video file to YouTube will pre-process it and maybe adjust the bitrate or the resolution, and then convert it to several kind of resolution for later streaming. On this slide, I would like to introduce several video API on Linux and that support hardware acceleration. The first is VA API, or we simply call it VAPI, which stands for Video Acceleration API. It was originally designed by Intel, and today it is remain the primary and actively support cross-vendor hardware video API on Linux. VAPI support a wide range of operations. On decoding side, it converts formats such as MPEG-2, MPEG-4, PAR2, VC1, H.264, H.264, HEVC, VPA, VP9, AV1, as well as JPEG and motion JPEG. For encoding, it supports MPEG-2, H.264, HEVC, VPA, and even AV1. It also provides video post-processing features. Next, we have VDPAU or VALPAU, the video decode presentation API for Unix. This API was originally created and maintained by NVIDIA, and it is still used by many Linux users today. But its role is gradually shrinking. NVIDIA has stopped adding new features and is shifting toward NVDC and NVENC. As a result, it doesn't fully support modern codecs. AMD and Intel only offer translation layers instead of a native VDPAU support, further limiting its future potential. The last API set is Mocha Video. It is a more recent API focused pure on decode and encode operations. Unlike a VA API, it does not include video processing capability. It's considered emerging standard, offering cross-vendor support with a unified interface for both decoding and encoding. More importantly, it aims to support modern codecs such as AV1 and HEVC and H.265. So overall, VAPI is currently the most mature and feature-complete option. VALPAU is older and declining, and Mocha Video is an emerging path forward for modern hardware video workload on Linux. Okay, the second topic is overview of AMD 2D hardware acceleration. On this slide, I will walk through AMD's video acceleration component and the architectural motivation behind them. Let's start with VCN, or Video Core Next. VCN is AMD's fixed function video engine responsible for encoding and decoding. By offloading these operations from CPU or GPU, we can eliminate unnecessary compute load on 3D engine and significantly improve power efficiency and throughput. The next hardware is MPO, stand for multi-plane overlay. MPO allows the display controller to composite multiple hardware plane directly without routing everything through the GPU. A typical example is decode MV12 surface instead of performing MV12 to RGB conversion. Conversion, scaling, and composition via shaders. MPO can present them directly from scan-out engine. This avoids 3D engine wake-ups and reduce memory bandwidth consumption and keep power usage low when playing video. However, this architecture has constraints. MPO has limited layer count and scaling ratios. And the multiple display setup might disable MPO entirely. So for this reason, this lead to the need for dedicated 2D video processing block, VPE, stand for video processing engine. VPE is introduced to offload post-processing tasks that were previously shared bounded and enabling low power operation before co-working. Better co-working with VCN. With VPE in place, we can maintain hardware accelerated path from decode to display without falling back to shader composition. So let's move one layer deeper into the architecture of AMD 2D hardware acceleration itself. It's currently integrated in some of the lately AMD's APU products, and then will be integrated in future discrete GPUs. The VPE subsystem is composed of two main hardware blocks, VPC and VPEP. First, the VPC is for control and the DMA engine, which is derived from AMD's SDMA design. This is co-worked with GPU to transfer the memory from device to host or vice versa. You can think of a VPC as a control and scheduling brain of a VPE pipeline. It manages clock, power, and reset domains, and in enabling aggressive power gating and quick ramp down while workload arrives. It's also coordinate memory access by instructing reader and writer units to fetch or commit surface plane to memory according to the processing plane. A VPC also execute command streams supporting tiling and detiling to the hardware, and can operate efficiently with GPU memory layout. This part is also firmware driven. A microcontroller consumes command from a ring buffer, and it can schedule multiple hardware queues with priority and bandwidth awareness. This allows the system to process multiple video tasks concurrently. Then we have VPP, VP processing pipeline, built from AMD's DCN component. It's a major component of AMD's display hardware. And VPP is where the actual pixel level operation happens. And it's supposed commonly use video and display formats such as MV12 and P010 ARGB with 8 or 10 bits and FP16 and 32-bit packet RGB, and can convert in both SDR and HDR case. Inside this pipeline, VPP can perform color space conversion, scaling, blending, and gamut remake, and tone mapping, and programmable gamma. So instead of pushing this operation to shader, which costs power and add latency, this fixed function blocks can execute them deterministically and with higher throughput. Okay, and the next topic is our plumbing works in software stack. First of all, let's check an overview of VA API. So, which is currently the primary hardware video interface used across the Linux system. VA API can be viewed as a two-layer structure, a front end and a back end, with the applications sitting above the front end layer. Let's start with the front end component, DVVA. This is the public API interface that is exposed to application when a program requests hardware video acceleration. DVVA detects the underlying hardware capability from the display system. For example, in the DRM system, and then load correct user space backend driver. It does not provide video itself. Instead, it acts as an abstraction layer that keeps application vendor agnostic. And below that, sorry, below that is the backend driver layer. This is where the vendor-specific logic resides. For AMD, along with legacy Intel and Nouveau, the backend is implemented through Mesa. Mesa handles video-related operations and pass requests to hardware engines such as VCN and VP or VP. Modern Intel platform also support a separate driver or user space driver, which name is Intel Media Driver. It does not rely on Mesa and directly target to Intel's own hardware more efficiently. Above this stack are user application. VA API support is present in nearly all mainstream video application on Linux, including FFmpeg and MPV player, video LAN, or in short, VLC, and coded media system. And the two major browser in the market, which are Chrome and Firefox, and Jellyfish Media Service, and OBS Studio, etc., etc. Now that we have seen WAPI code flow in detail, let's summarize how typical application use WAPI in practice. You can think of the pipeline in three main stages. Initialization, and the second is capability query, and then the last one is main processing loop. The step one is initialization, which used to set up display and context. And the application starts by opening a display connection and initializing the WAPI. This is where we call VA initialize. The function that starts with lowercase VA is part of WAPI codes. And VA initialize detect hardware and load the corresponding backend driver. And then we create a codec or video processing context, which prepare surface buffer and the internal VC and VP resource. And step two is acquiring the hardware capability. And before stream video frames, application usually query the feature, what feature are supported. For example, maximum input-output resolution and scaling ratio, or the supported color conversion format. And then the major step, that's step is entering the main loop. Once initialized, the application enter its main render loop. Here is where we repeatedly feed bitstream slice or frame into the pipeline using WAPI codes like VA begin picture, VA render picture, and VA end picture. And then synchronize with VA sync surface to retrieve process output. This loop continue for every frame with hardware doing the heavy lifting under the hood. Yes.
Okay, so so far you are talking about VA API, but what about the embedded use cases? Because there's a lot of 2D accelerators on embedded systems. Is there any way to expose those either directly by the kernel or through Mesa to user space via some unified API? I mean, all these embedded systems, every one of them has some sort of a 2D accelerator which does color space conversion, scaling, rotation, this kind of stuff. So is there anything in the kernel or in Mesa that would give us unified interface to these devices?
We was thinking about video for DNS too. But because one important part of our user space library is to build the command for our hardware, just like GPU. They allow the user space program called OpenGL, and then build GPU command string, and then sent to the GPU driver.
But then, for example, the Vivante IP, this is actually part of a GPU as well. So how would that look like? Would you have the 3D part of the GPU as a DRM device and the 2D part of the GPU as a V4L2 device, or how would that look like?
So this is related to the question that was asked, and I think you kind of got the notion there. I'm kind of curious, if you have a graphics device that has a separate video accelerator and you want to expose it, and let's say it has no display out, you could have the graphics component be a separate render node from the base DRM device node, and the base DRM device node implements ioctls that can power true or plumb true the video accelerator. And so when you go through VA API, through user space and all that, it goes through that path on the default device node, and then for other graphics application, to use the render node. Would that model work?
Okay, so the Vivanta driver already has something like this. I mean, you can open effectively either pipe. Mesa opens the 3D pipe, and then it can do OpenGL, right? But there is the 2D pipe, which effectively, if I want to use it, I have to hand roll me the command stream and just flush it in there, and it does something. But what I am curious about is if there is some sort of a unified API to this, because I mean, this kind of 2D hardware exists on multiple embedded systems, and there is literally nothing for a decade now.
There's a fairly recent effort. Paul Koshalkovsky has made a presentation at XDC this year, where he's proposing a new user space library. So the kernel API would tie to DRM most likely, but anything could be used. And he has a proposal for user space API for that. That wouldn't cover video encoding and decoding, but the 2D acceleration, bleeding engine, resizing, and things like that. At the moment, it's just an idea. There's no implementation, but it seems to be interesting.
Like at this stage, if someone was going to do a 2D acceleration, I think it'd be crazy to not just do it with Vulkan. I think it would be, it would be a new level of insanity to develop anything that wasn't just another Vulkan API. That just, because Vulkan now is like, you don't need any, like it's capable of no compute, no graphics, no anything. It's just, you can just do video, you can just do compute, you could just do this. You know, like if you're going to do a API, like for hardware that has a front end, like a queue that you can actually record commands for, and then submit to the device, where you don't have to just directly poke registers, Vulkan is the right answer. For stuff where you're poking registers from user space, or you have to poke registers in the kernel, I don't have a good answer for that. But it would be crazy, because doing Vulkan, when we did video in Vulkan, it makes so much sense that when you see the pipeline, the graphics, and the video together. It's pity we haven't fitted this into Vulkan yet. I think there has been, I don't know if remember, I think there has been some proposal from AMD to talk about this, but I don't know how far it's gotten.
Yeah, okay. But how does this fit with the embedded devices, which may not necessarily do Vulkan? I mean, these embedded GPUs may be just OpenGL, yes, or some such. Would you still be able to at least use the Vulkan for the 2D part?
One reason why Vulkan may be a bit annoying is that you'll need to go through Kronos and establish a working group to create an API.
While that is annoying, you know what the other side of that is? We have had nothing for 15, 20 years. So maybe if we'd gone through the working group, we might have gotten something. I don't know. Or maybe if we just did it as an extension that was in Mesa only and then showed the way, they would take on that.
You know, agree. Maybe a community effort for an extension, and then maybe it's going to be standardized after that. That could work.
Like I implemented all of the Vulkan, the video decode for like, I think I did H.265 and AV. Oh, I did VP9 and AV1 before Kronos did it in Mesa as extensions, and then Kronos took my Mesa AV1 and VP9 decoders and wrote the proper one. So it is possible to do.
One follow-up before we get back to the talk. I think Vulkan video for embedded does make a lot of sense. I think the one concern that users will have is a lot of applications will implement VA API today, and they're moving to Vulkan video, but that adoption may not be there. But I think long-term, what was discussed does make a lot of sense. Right, but I guess what I'm saying is, if the direction for embedded was to, support Vulkan video, even then, for users to take advantage of that, that might take time as well. Yeah. Can take this off. Oh, yeah.
Yeah, I don't think the Vulkan video is going to happen because the VPUs are generally separate IPs.
There has been an effort. I can't remember who started it, but there's been a couple of suggestions to try, and I don't think where everyone's to do Vulkan on top of v4L2, like to just implement the Vulkan video decoding extension on top of the v4L2 as a generic as possible there. And I understand that might be a hand waving, but I know at least 2 people have suggested we should do that, and I've started looking at it and then realized I didn't have a device to play with, and I went, okay, I'll get back to it. And then someone else said they were looking at it. So I know 2 people have actually interest in trying to see if that's possible to implement the Vulkan video APIs on top of v4L2, whether we would use a CPU queue or whatever. I don't really know what the plan was, but.
Okay.
Thanks.
So for this page, I will explain how it looks at how AMD VP integrate into the full software stack. The diagram shows end-to-end flow from application at the top through Mesa in user space. The yellow arrows indicate the GPU path, and the magenta arrow indicate the VPE path. Now, traditionally, the video post-processing is achieved by the module of Mesa, which is auxiliary VLO module. It contains a bunch of generic shader for doing scaling and color conversion and other kind of bit-breaking operations. And while the system decide to switch to VP, and the 2D acceleration jobs will be performed by Radiant SI module inside the Mesa, which is AMD's Radiant SI, and then goes down to the yellow block of our VP lib to generate the VP command string, and then down to the firmware and the hardware. So the implementation of AMD's VP lib is implemented in C and shared between Linux and Windows driver, and it used to construct a command buffer based on video processing requirement. You can see the below table. We only have 5 functions to do the relative job. The most important one is VP build, VP bridge. It will generate tons of VP command and then send to the ring buffer for later execution. Yeah. And for this page, this is the major flow diagram about VA render picture. It illustrates how user space broken from VA picking picture and VA render picture, and goes down to the very bottom of AMD's sub module to reach the VP lib. Sorry, I'm about running out of time. This is a VA in picture. The last page is about how the command is built, and for this page is how the command, the built command is submitted, and it was submitted by the Win system of a Mesa system, and then submit from DIMS IACTO, and then finally reach our VP driver. For this page, I'm going to explain the two different paths that MPV player playing the HDR videos. For the GPU way, MPV will firstly read the video HDR metadata, include transfer function, color standard, and other necessary data, and combine with display HDR data to generate 3D lookup table if required. And then the data will send to Mesa, and together with decoded frame, which decoded by VCN, and then render and send out to the scan out display. For the VP way, the 3D log was calculated in different place, and this is because the path that MPV, the code path that MPV is hard, a little bit difficult to be reused by us to for 3D dot and other HDR tone mapping process. So we decided to calculate 3D dot with our own library, which is GMDIP, to generate the required data into VP and do the final tone mapping playback. During the enablement of MP, we made a lot of problems. And first, MPV does not pass HDR metadata or 3D lot information to Mesa. And this means even if MPV generates lots of HDR metadata, the information never reach the VP end. And then Mesa currently lacks support of receiving 3D lot through VA API. In fact, VA API does defines the interface of passing 3D lot. However, there's no existing 3D lot filter implementation in Mesa video processing stack. So even the metadata could be forward, VP lib would have nowhere to consume it. For VP kernel toner driver, it is a relatively simple part because most complicated job is performed in user space driver. And here it only provide to major functions. First one is comment submission. It is measure ring buffer and with share code of MD-IPs. It uses unified DRM IACTO of submission for MD's GPU and VCN and VP. And then the second function is power and clock gating. Based on the workload, perform the dynamic power measurement with VP firmware for S0, S3, and the Z8 state. So this is the power consumption part of our measurement recently. It is measurement in a laptop that equipped with MD's VP. You can see let's show you the points. And if we play back with default setting, which the hardware acceleration is not enabled, it will consume 20 watts of power. But if we enable all required feature, we will reach 9.5 watts. It seems a little bit more than this one, but the playback result of this item, the DMA buff only item is lack of proper HDR tone mapping, so you'll be look like a little bit washed out. So let's price the challenge and the call for collaborations. The first challenge is adding new color formats, and it is a growing challenge that we have to add in new color format for DBVA and Mesa. It is a time-consuming job to discuss and back and forth with community, but can I finish? Okay. 30 seconds. So, okay, I skip some of them. I hear you talk about Vulkan support, and we discuss about Vulkan support, and we find out VK command copy image and VK command bridge image does not support color conversion and blending, and it cannot fully reflect the complete capability of a VP. So we were thinking about other alternative way to support Vulkan, maybe a new API or new extension. Okay, thank you. Or maybe like
any questions?
Maybe let's discuss offline.
Yeah. I like. What?
Did you try to integrate these formats and these like matrices into Mesa? So was there communication with the Mesa people about that?
We're just getting started. We're just getting started to survey the potential possibility of a Vulkan extension. So yeah.
So one thing on the embedded hardware, I'm not always sure what, like, so one of the big things on the AMD hardware is, like, of course, there's the VPC thing that, you know, you submit the user space command packets to, they're all generated in user space, and then it just does all of that. Do all the embeddeds, like I was like, I know on things like RPi with 3D engine, it's not the same. Like, you end up doing all that in the kernel, and you know, it's like, is it the similar model in those that there's actually an engine with firmware that does that stuff, or do you have to submit it from the main CPU and do that in the kernel for on the embedded devices? The hardware model for programming the video engines and the 2D engines on these, is it like a command submission model, or is it a direct programming model? Yeah, for you.
Hey, so I'm familiar with the Vivante IP. The Vivante IP, you just generate a kind of a command stream, put it into a DMA buff, and then say, okay, to the engine, go do something in the memory. And it does memory to memory something. It's like a fancy DMA, basically. Hey, it has some support for chaining DMA descriptors of sorts. So you can basically say, okay, here's a bunch of DMA descriptors and they are connected, and you say, okay, run. It will go to the end, or maybe there is some flag which says, okay, stop here, and the CPU is still preparing the rest. You can get an interrupt that it got somewhere, that a completion happened. But it's probably simplistic.
Yeah, the sync points on host 1x, they are exactly like that. So they basically run a command stream with the operation that you want to do, and then you at the very end you add an increment for your sync point, and then you can have different command streams listening for that sync point increment, and you can also generate an interrupt when that happens. So we've never made that work in the upstream context, but you can theoretically make the display wait on a sync point so that it can then wait for that frame to become ready and display it or flip to it. So one other question is that came to me is because we've seen this like 2D acceleration APIs mentioned in the past, but it seems to me like today we don't really care too much about blitz in general, but more about video processing, like having this kind of hardware used as a way of scaling video frames and so on. So is that still like the main case that we want this for, or do people still care about like acceleration?
I think what I care about is scaling, maybe a little bit of rotation, and definitely compositing. Accelerated compositing would be really, really nice. Because doing it on a 3D GPU is just consumes a lot of power and it's wasteful.
So your concern is vAPI is too heavyweight to you.
No, for me, vAPI is not an option because on embedded systems it doesn't exist. So
would it be interesting to bring it to embedded systems? Laurent?
I don't know. You can technically, and maybe you know this better, Dave, but I think you can get VA API support if you implement the correct bits in Mesa. I think there's like a pipe video thing that you can implement, right? And then you can get VA API for free. There's quite a bit of work involved to get it to that point, but I don't know if it's really useful if you don't have the rest of the video pipeline, because then you'd have to find some way to export it from or import it into VA API just to do the scaling and color conversion. You might lose some of the benefits that you get from the hardware acceleration.
Is there anyone use the API from V4L2? It still have some kind of built-in API, but currently we cannot support it because our user space library is difficult to transfer to be put into kernel space for comment generation. It's a
I was just saying, Laura, one other thing that like has just landed now on the DRM side is we've added this whole color management pipeline, which is kind of like this on the output side. It's like, it's got color conversions. It's got all of the pieces used on the display output pipeline to do all of the, not, when you definitely know it's going to the display, not, it's not used to be going to send it across the network, right? But we've designed that set of APIs and it's just landed for like AMD and Intel. So like there's something there maybe that, if we can design something similar would be a good idea, because like it's not, I don't think it's a direct, you have to implement it exactly like this. It's more of a describe it and then whatever the hardware does, what the hardware does. Compositing has always been, that's where, like I think the only one we tried to cheat on, I think, is I think the RPi we can composite on, but only because they did some KMS thing that's kind of messy, or it doesn't really translate for everyone. But yeah, I don't really know how you're gonna fit where we'd fit compositing into the standard pipeline, partly because of the fact that it depends on your compositor to support it, and then you have to get into compositors. That's a battle all by itself. And all the current compositors are like, no, it's not even Vulkan compositors really. Like only GameScope might be the only one that actually uses Vulkan. Everyone's still using OpenGL for compositing, so it's a pain in the ass to add anything else. That will change, but right now it's still OpenGL based.
What we were done with the official part. Is it possible to is it possible to have like a very minimalistic Vulkan driver that does nothing but scaling, color conversion, that kind of thing, or?
I think that would be the tricky bit to figure out, is that like, right, so yeah, originally Vulkan you couldn't do anything without having some, but now they've added all the different pipeline queue types, and you can actually have a Vulkan driver that only does video decoding queue or video encoding queue without doing any of the compute or graphics queues. But you would then have to define enough an extension and a queue type for what that would be. And like for VPE, it probably would make sense to have a VPE pipeline type, but then how do you, of course, you'd have to expose all the different stages you have or how they hook them together and stuff. But yeah, if you can get it into a thing that's a queue that like a representative, yeah, you could just expose that as a singular device. And I think I think one vendor currently was thinking of shipping a Vulkan video only driver for like, as one of their things. So it's definitely possible now. It used not to be possible, but it is now.
And there's work as well to try to make Vulkan more modular, to ease that, because initially it was very tied to 3D acceleration. And so using Vulkan for video decoding or encoding, for instance, having to implement lots of things related to 3D acceleration, it makes sense. So that's in progress, and that should make things easy as well.
Exactly.